मंच एक खुला मंच है, आए जब भी चाहे। किशोर मंच एक खुला मंच है, आए जब भी चाहे। हर किशोर को मिलेगा अवसर, खुलती जाए राहें। आए जब भी चाहे, आए जब भी चाहे, आए जब भी चाहे, आए जब भी चाहे। हो कला सामाजिक ज्ञान, भाषा गणित या हो विज्ञान, कठिन नहीं है विषय कोई भी, करो जरा सा ध्यान। हो कला सामाजिक ज्ञान, भाषा गणित या हो विज्ञान, कठिन नहीं है विषय कोई भी, करो जरा सा ध्यान।
ये है
किशोर मंच।
In the last lecture, we dealt with Kirchhoff's laws. As you might know now, that these laws are an easy way to calculate currents, voltages, resistances in the various components of an electrical circuit. Today, we start with magnetic effects of currents, and we shall find out the magnetic field of currents in various shapes. You are familiar with magnets. Most of you might have even played with them. Every magnet has two poles. An important fact to remember is that no magnet has ever been found with one pole, or an isolated pole called a monopole. This implies that whatever the conditions, each magnet must have two poles. If we cut a magnet, the two portions of that cut magnet also have two poles each. Even at atomic scale, an elementary magnet has two poles. This is in complete contrast to electric charges, which can exist in isolation. I mean, you can have positive charge, you can have a negative charge, but here each magnet must have both the poles. You can't have an isolated pole or a monopole. For practical purposes, however, poles at the end of an extremely long bar magnet, you have two very long bar magnets, and these two can be considered as isolated poles, and then the force between them is given by this. The force of attraction or repulsion between magnetic poles is similar to the Coulomb force between charges. Here also, like poles repel each other and unlike poles attract each other, and the force between the two poles is mu 0 by 4 pi into m1 m2 by r squared, where m1 m2 are the strengths of the two poles and mu 0 is the permeability of free space or vacuum. Remember that mu 0 and epsilon 0 are related to each other through the velocity of light. C is equal to square root of 1 by mu 0 epsilon 0. Remember, epsilon 0 we used in the electric field. An important property of a magnet is that when suspended freely, it always settles in the north south direction. That is, if I take a magnet here, then suspend it freely, then it will always settle in a direction which is north south, which points towards north and towards south, as shown here. The pole which points towards north is called the north pole of the magnet, and the pole which points towards south is called the south pole of the magnet. Remember, each magnet must have two poles, it cannot have one pole. It is this property of settling in the north south direction that made a magnet a navigational aid for travelers on land and on sea. You see, in ancient times, you could find your way, you could find your direction with the help of magnets. That is why they were called navigational aids. For this purpose, a small magnetic needle is mounted on a pivot, so that it can rotate freely in the horizontal plane. Such a needle is called a compass needle, and you must have been familiar with these needles. Strictly speaking, a freely suspended magnet points in the magnetic north south direction, not geographic. You see, here I have shown both the directions. The north south direction, which is geographic, is the actual axis of rotation of the earth. The magnetic axis, here is a magnetic north and magnetic south. This line joining the magnetic north and magnetic south is called the magnetic axis, and this makes an angle of about 11 degrees with the north south direction. This angle changes with time, but at the moment this value is about 11 degrees. Like the force of attraction or repulsion between charges, the force between magnetic poles is explained in terms of a field. In this case, we call this field a magnetic field. We say that a magnet creates around itself space or magnetic field, in which if another magnet or a current carrying conductor enters, then that body which enters will be affected by this field. This is called the magnetic field, and magnetic field is represented as electric field by what are known as magnetic field lines. It must be remembered that the field lines are only imaginary lines. No such lines actually exist. They are used simply to map a given magnetic field. The following are some of the properties of the magnetic field lines. A field line starts at a north pole and ends at a south pole. Here it ends at a south pole. This will also end at a south pole, and inside the magnet these lines go from south to north, so that these lines they form complete loops. That is important. We shall see why they form complete loops, but for the moment remember they form complete loops. At any point on a field line, if I want to find the direction of the magnetic field, I draw a tangent at that line, and the direction of the tangent gives you the direction of the magnetic field at that point. The relative density of field lines, it dictates the strength of the field. These lines, for example, and these lines are denser than these, and therefore, this field is stronger than this field. Straight and equally spaced lines indicate a uniform field. These lines are parallel and equally placed, therefore, they represent a uniform magnetic field. Another important property is that there is tension along the length of field lines. If this is a field line, then this field line acts as a stretched spring. That means, if I leave it, it tends to come back. So, they always tend to shorten their length, and in this process they cause attraction between unlike poles. Here I have drawn magnetic field lines of two poles, two bar magnets, south pole here, north pole here, and the lines go like this, and these lines tend to shorten their length, and therefore, there is this force of attraction between the two magnets. Also, the field lines exert lateral pressure, that is sideways pressure, and this results in the repulsion of two like poles. Here I have got north pole, lines go like this, lines go like this, and wherever they are in the neighborhood, there is repulsion, there is pressure pulling them apart, and this gives rise to repulsion between like poles. Let us learn some history. In 1820, the Danish scientist Ørsted showed that a magnetic needle kept in the vicinity of a current carrying wire gets deflected. This may be common knowledge today, but it was first discovered in 1820 by Ørsted. This was a clear demonstration that the current carrying conductor was behaving like a magnet. That is, if you have a conductor which carries current, then it behaves like a magnet. Remember that at that time the only magnets known were the natural magnets, lodestones, or made from iron. So, the fact that an electric current could be a source of magnetism was a very important discovery. Following Ørsted, the French scientist Ampere performed a series of experiments with currents carrying wires. He showed that the magnetic lines of force form loops, we shall see that in a moment, loops round the wires which carry current. He also explained the sense in which the loops of field lines are wound round the wire, and then the direction in which they are wound. We shall find that in a moment. The field lines follow what is known as the right hand thumb rule. That is, if I take my right hand and stretch my thumb like this is the direction of the current, then the way these fingers are wound, that gives the direction of the magnetic field lines. As shown here, stretch your thumb of the right hand, then you see how the fingers are wound, and that gives the direction of the field lines as shown here. Following the discovery of the magnetic field due to a straight current, Ampere argued that two straight wires carrying parallel currents would attract each other, while those carrying currents in opposite directions would repel each other. You see, these are the two wires carrying current in the same direction, there is attraction between them, and here are two wires carrying current in the opposite directions, and they repel each other. Ampere also proposed a law known as Ampere's circuital law, which enables us to calculate the magnetic field due to current sources. You see, we have seen that currents are sources of magnetic fields. So, Ampere proposed this law, which allows us to calculate the magnetic field due to various currents. The law states that the line integral along a closed loop over the component of magnetic field parallel to the loop is mu 0 times the total or net current passing through the surface S spanned by the closed loop. Let me explain. I have a loop C here, I have a loop here. This loop spans a surface and the currents are going through this surface, this way or that way. And if I take the component of magnetic field parallel to the direction of the loop, then the integral B parallel over this loop gives us mu 0 times the sum of currents which are passing through this surface which spans this loop C, explained here in greater detail. You see, B parallel is the field, B is the field, and B parallel is the field which is along the direction of the loop. So, B parallel times d l, the integral of that, the line integral of that is equal to mu 0 times the sum of the currents I 1 plus I 2 plus I 3 etcetera, which are passing through the surface S. In the present case, after taking due account of the directions of the currents specified by the anti-clockwise direction of the loop, you see, we have to determine which current is positive, which current is negative, because we said algebraic sum of currents. How do we find that? We use the right hand thumb rule, and here this loop C is in the counterclockwise direction, therefore, the current in this direction is positive, the current in this direction is negative. So, I 1, I 2 are positive currents, I 3 is the negative current considering the direction of this loop. That is very important, that you apply the right hand thumb rule, find out which currents are positive, which currents are negative, and then in this case this sigma I gives I1 plus I2 minus I3, and mu 0, let me remind you, is the permeability of free space. Its value is 4 pi times 10 to the power minus 7 T m a minus 1. In vector notation, Ampere's law is written as B dot dl. B dot dl is obviously the parallel component. So, therefore, B dot dl is equal to mu 0 times I enclosed, all the currents which pass through the surface enclosed by the loop. This law is the magnetic analog or counterpart of the Gauss law in electrostatics. Let me remind you, Gauss law in electrostatics was B dot ds, where ds was the element of the surface, and B dot ds is the flux through this element of the surface. So, the total flux, that is the integral of B dot ds, is equal to q, the charge enclosed within that surface, divided by epsilon 0. The evaluation of the integral in Ampere's law becomes easy if there is some symmetry in the system. Recall that for Gauss law also, for the application of Gauss law also, we needed some symmetry. So, here also we need some kind of symmetry to make it possible to apply Ampere's law. Let me immediately take an example to fix the ideas of these loops. I have 3 currents, this blue one and 2 red ones. The red ones are coming out of the plane and the blue one is going into the plane, and I have got 3 loops here, C1, C2, C3. So, let us take the first C3. C3 is anti-clockwise, and therefore, the current going into the plane is a positive current. Therefore, if I take loop C3, then integral of B dot dl in that loop is equal to mu 0 times I. For the loop C1, B dot dl is equal to, for the C2, this loop is clockwise, and therefore, the currents coming out of the plane, they are positive currents. Therefore, B dot dl is 2, because there are 2 currents, equal currents, 2 mu 0 I. And let us take the third loop. Third loop is, we have dealt with C3, C2 and C2. C2, there are 2 currents which are equal and opposite. Therefore, the net current is 0. Therefore, for the C2, B dot dl is equal to 0. For C3, B dot dl is equal to mu 0 I. For C2, B dot dl integral of that is 0. For C1, B dot dl is equal to 2 mu 0 I. The important thing is that considering the direction of the loop, you must find out the positive direction of the current. What happens in the above problem if the loop C3, for example, is clockwise? Let me show you loop C3 again. C3 was anti-clockwise. Suppose I make it clockwise, what happens? Then this current becomes negative. With respect to the direction of the loop, this current becomes negative, and therefore, the integral of B dot dl becomes minus mu 0 times I. So, every time you have to determine the direction of the current, whether it is positive or negative, considering the direction of the loop. As an application of Ampere's law, let us find the magnetic field due to a straight current at a distance r from it. So, I have a straight current at a distance r from this current, I want to find out the field. Remember that I am taking a very long straight current. In fact, theoretically it should be infinitely long. If it is so, then there is symmetry all around the current except at the points near the ends. So, we are not worried about the ends, we shall take somewhere far from the ends. There is circular symmetry also, because there is a straight current, therefore, there is a circular symmetry. So, with these 2 symmetries, the longitudinal symmetry and the circular symmetry, let us see what we get. We take this current, and we have seen already from Ampere's work and from Oyster's work that the field lines would form a loop. So, let us imagine there is a loop, and this loop is drawn with the radius r, the distance at which we want to find out the field, and then this loop, considering this current, I have taken this loop to be in the anti-clockwise direction, again using that rule. Because of symmetry, the magnetic field must be constant along this loop. It cannot be across that loop, because then dot product becomes 0. So, it must be along the loop and must be constant because of symmetry. Therefore, I have got the Ampere's law B dot d l is equal to mu 0 I enclosed, and I use that law. This the length, total length of this loop is 2 pi r. So, 2 pi r, you see in the integral B dot d l, B is constant. So, I can take it out, and integral of d l is simply 2 pi r. So, we have 2 pi r B is equal to mu 0 I, which gives B equal to mu 0 I by 2 pi r. So, the magnetic field due to a current, straight current, is equal to mu 0 I by 2 pi r at a distance r from the current. And again, I have repeated it several times, you can find that if the current in this direction, the loop must be anticlockwise. Let us take another case. Suppose a solid cylindrical conductor, we took a wire, suppose there is a rod of a certain thickness, and let us find out the magnetic field due to that rod. So, what we do is, this is the cross section of the cylindrical conductor of radius a, and I draw a circle of radius r inside this cylindrical conductor. Remember that the current is uniformly spread along this cross section. Remember that. So, as the magnitude of the current is proportional to the area of the cross section, is uniformly spread, therefore, it must be proportional to the area of the cross section. Then for radius a, whose area is pi r squared and the total area is pi a squared, therefore, the current through this area spanned by this radius r is I r equal to I times r squared by a square, simply proportional to the area for r less than a. Now, you consider the loop of radius r, and what we do is, we again, because of symmetry, the magnetic field must be constant. The integral of d l in this case would be 2 pi capital R. So, 2 pi capital R times B r, the magnetic field at a distance r from the center of the axis of the cylinder, that is equal to mu 0 times I. Therefore, B r is mu 0 I by 2 pi a squared into r. I here is I r. Remember, I r is I r squared by a squared. Therefore, 2 pi r B r is equal to I r times mu 0, and therefore, B r is mu 0 I by 2 pi a squared times r. What about the field outside? At the center r is 0, this radius is 0, therefore, field is 0. At the boundary r is equal to a, therefore, 1 a gets cancelled, and therefore, B r becomes mu 0 I by 2 pi a. So, it becomes mu 0 I by 2 pi a. At r greater than a, the whole current is included, therefore, the application of Ampere's law simply gives you B equal to mu 0 I by 2 pi r, which again is all right if I put r is equal to a is the surface, and r greater than a, all the current is included. Therefore, 2 pi r times B is equal to mu 0 I. Therefore, at a distance r is equal to B is equal to mu 0 I by 2 pi r. If I put r equal to a, then I get the magnetic field at the surface of the cylinder, which matches with what we have found earlier. Here I am showing the profile of the magnetic field. We have got magnetic field here. This is the radius a of the cylindrical conductor, and this is r distance outside the radius, and this varies as 1 by r. We have found that the magnetic field outside varies as 1 by r. Therefore, this is 1 by r curve. This is a straight line which shows that within the cylinder the magnetic field is proportional to r. So, therefore, we have got magnetic field directly proportional to r, linearly proportional to r, goes up to a, and then the field decreases by 1 by r. We just found that. So, by use of Ampere's law, we have been able to find magnetic fields due to a straight current and also due to a straight cylindrical conductor. In the next lecture we shall continue with the Ampere's law, and we shall also find the fields due to a solenoid. In the last lecture, I introduced Ampere's law. The full advantage of Ampere's law can be derived if we have some symmetry in the system, and using that symmetry we found the magnetic field due to a straight long current and straight long cylindrical conductor. We will continue in this lecture with Ampere's law for some time, and then we shall find the fields due to the devices like solenoid and toroid. So, as another example of the application of Ampere's law, let us take now a long cylinder which is hollow, that is, it has certain thickness, there is an inner radius and there is outer radius, it is hollow. Inner radius is A and the outer radius is B, as I have shown here. And so, what do we do? Again the current is constantly spread over this cross section. So, once again I take a circle of radius r which is inside the conductor, that is r is greater than A, and find the current in the cross section drawn by radius A, and I shall use that. But let us first take a simple case. We draw a Ampere's circle inside the conductor, that is, the radius of that is less than A inside the conductor, and since there are no currents inside, the magnetic field there must be 0. For r 1 less than A, 2 pi r 1 times B is 0, therefore, B is 0. Now, I choose the circle of radius r inside the conductor, and first of all the current density would be total current divided by the area of cross section, which is pi into B square minus A square. So, therefore, the current density is J equal to I by pi into B square minus A square, and therefore, the current inside this circle of radius r is simply pi r square minus A square, that is the area, into J, the current density, and that is equal to the expression which we shall use. This is the expression, and because of symmetry the field must be constant. Therefore, 2 pi r times B in the shell, because the radius is in the shell, that is equal to mu 0 times I into J, the current density which we used earlier. So, we get 2 pi r times B shell is equal to mu 0 into I threading this circle r or within this circle r, which if we use that expression gives us mu 0 into pi r squared minus A squared by pi B squared minus A squared into I. So, therefore, this pi gets cancelled and the magnetic field inside the shell, that is, for radii between A and B, the field is mu 0 times r squared minus A squared by 2 pi r into B squared minus A squared into I. Now, let us take a loop which is outside the cylinder, r greater than B, this outer circle of radius r, and r is greater than the outer radius of the cylinder. Within this circle, the whole current I is included, and therefore, we simply have 2 pi r times B equal to mu 0 I, or B equal to mu 0 I by 2 pi r. And we can now see that this expression mu 0 I by 2 pi r gives us at the surface the same field as the expression we found for the shell. This is easy to verify and you can do it. For the field outside this conductor, we take the Amperian loop of radius r, small r, which is greater than the radius, outer radius B of the cylinder, and this circle includes all the current which is there in the conductor, the whole of this current, and therefore, and because of symmetry, magnetic field must be constant, and along the loop Therefore, the integral B dot dl is simply 2 pi r times B, and that is equal to mu 0 I, because this loop includes the whole current, and therefore, we get B equal to mu 0 I by 2 pi r. So, that is the magnetic field outside the conductor, and you can check that at r equal to B, this capital R equal to B, you get the same result. This is important because the field outside and field inside, they must match at the surface. There cannot be any discontinuity. Also, the field inside here at radius a must also become 0, because inside there is no field. So, there at each point there must be a continuity. You cannot have discontinuous magnetic fields. And here I have sketched the magnetic field inside the hollow, then in the shell, then outside. Outside it varies as 1 by r, within the shell it varies as this, and in the hollow the field is 0. Again I repeat the same thing, but you know that how to find the direction of the magnetic field given the direction of the current, or given the direction of the loop, how to find the direction of the current. This is again given by the right hand thumb rule. For a current in the form of a circular loop, the magnetic field can be found by considering the loop to be made of infinite number of small segments. That is, I break this circular loop into sections, infinitely small sections of the current, and each is a straight section. Therefore, I have found the magnetic field due to a straight current. Therefore, I apply that result. So, this is a loop. I take two diametrically opposite segments shown in red here, and these are straight, and therefore, the loops are formed around this, and you can see that what happens because of this diametrically opposite, the field at the center of the loop is in this direction, is perpendicular to the plane of the loop. That is important thing to remember. And now we can find the magnitude of this field also. Not only is it true of these two, this is true of all diametrically opposite elements. They all reinforce the fact that the magnetic field at the center is perpendicular to the plane of the loop. And in fact, the loop acts just like a bar magnet or a short bar magnet or a dipole, magnetic dipole. And how to find the poles we shall see in a moment. But a current loop acts like a very short bar magnet or a dipole, magnetic dipole. We shall continue from this, that each loop represents a small magnet, and the lines or field lines are perpendicular to the plane of the loop. So, let us now take a magnetic field due to a solenoid. Solenoid consists of several loops carrying the current, and if we use this fact that there are now several loops one after the other and draw the lines of force due to each of these loops, then what happens? We find that the magnetic field at the center is reinforced. For all loops it gets added, whereas in the periphery, this, for example, the loop, the magnetic field is going downwards, here it is going upwards. So, they cancel. Here it is going again downwards, here it is going upwards, they cancel. So, at each place they are cancelling, only the magnetic field at the center is being reinforced, and at the periphery the field is actually very weak. So, the field due to a solenoid is along the axis of the solenoid, along the axis of the solenoid. The above argument shows that the magnetic field of a solenoid having several closely packed turns will be predominantly along the axis of the coil. The field outside the solenoid will be very weak, as I shown here. These are the loops, these will go outside and they are very weak. The field inside, perpendicular to the plane of the solenoid or along the axis of the solenoid, is very strong. If we take an infinite solenoid, actually such a solenoid is called an ideal solenoid. If we take an infinite solenoid, then infinitely long solenoid has translational and rotational symmetry. Translation, that I can deal with here, here, here without making any difference, because this is infinitely long, and also circular, because all these loops are circular, therefore, it has both circular symmetry as well as the translational symmetry. And all this shows that the field lines must be reinforces the fact that field lines must be along the axis. I have taken a very long solenoid here, and you can see the field lines at the periphery, that is near the edges, is very weak. It will make a loop here, but the field along the center is very strong, it is reinforced. So, for an expression we take an ideally solenoid, neglect, that means we neglect the effects at the edges, and this can be done as long as the length is much larger than the diameter of the solenoid. We shall assume that. And then we draw an Amperean loop. This side has length h, this side is of length AD and BC, and CD is of length h. And this is solenoid. I am showing the loops, and each loop carries current I. And we have already seen that the magnetic field must be along the axis. So, we take that structure, and now I take this loop and then I apply Ampere's law, and this applied to this loop, the Ampere's law says that B to A B dot dl plus C to B B dot dl plus C to D B dot dl plus D to A B dot dl, all that must be equal to the current inside this loop. And what is the current inside this loop? If there are n turns in the loop, then this must be equal to mu 0 into n into I. And now we shall evaluate these. It is simple. For B A the height is length is h, and for there is no current. So, therefore, the first one would be 0. For B C or C B and A D, the loop is perpendicular to the magnetic field. So, makes no contribution. The only contribution comes from C D, from C to D, B dot dl, and dl in that case is simply h. So, B dot h is equal to mu 0 n times I. That is what we have done here. B h is equal to mu 0 n times I, and therefore, B is mu 0 n I by h, and n by h is the number of turns per unit length. Therefore, B is equal to mu 0 small n times I, where small n now represents the number of turns per unit length. And you can see that because of this n is within my power, I can make n large or small, and therefore, I can adjust the field. In fact, solenoid is useful only because we can have fields of the strength we desire, and by making n as large as we need, we can make the field very strong. But there is a consideration, and that is that if I make n very large, the wire becomes very large, very long, and therefore, its resistance goes up. If its resistance goes up, then ohmic losses they go up, and also to make the current flow in this long loop with a large number of lines, large number of turns, I need a much greater voltage, and so on. So, the easier way is to use a core, of iron or a material like iron at the center of this solenoid. In that case, the magnetic field would be given by mu 0 times mu r times n times I, where mu r is the relative permeability of the core material. You see, you can start with B equal to mu times n I, where mu is the permeability of that material, and you can write this mu as mu by mu 0 into mu 0, and mu by mu 0 is the relative permeability. So, you get this expression, and mu r, the relative permeability for iron, for example, is more than 200. So, you can see that using such a core in the solenoid, we can make the magnetic field very strong. For fields stronger than even those achievable by iron core, special materials with high permeability have been developed. The core also concentrates the field lines and reduces non-uniformity of the field near the edges. This is very important. Usually, we neglect this effect. You see, if I put a core here then the core, we shall learn later that ferromagnetic materials like iron, they attract the lines of force. So, the lines of force, they present a low resistance path for the lines, magnetic field lines, and therefore, they prefer to go through the core. So, since the lines of these field lines tend to go through the core, therefore, the field is concentrated and in the axis of the solenoid. The direction of the field due to a solenoid is given by the familiar right hand rule, we shall apply here. If you are looking at a loop, say loop is like this and you are looking at the loop, then if the current in the loop is anti-clockwise, it is anti-clockwise, then the face which is towards me is the north pole, otherwise it is the south pole. So, if I look at a loop and the current in this loop is anti-clockwise, then I am looking the face of the loop towards me is a north pole and away from me is a south pole. You see here, as I have shown by the eye where I look, as I look, the current goes through this anti-clockwise, therefore, this is a north pole. If I look from this side, then it is a south pole. In any case, if it is a north pole, it has to be a south pole. We have found the magnetic field due to a solenoid. I want to repeat this. The important fact is that by the use of a suitable solenoid, we can get the magnetic field that we desire, and the magnetic field is concentrated near the axis of the solenoid, especially if there is a core of iron or material like iron. If you bend this solenoid, then it becomes a toroid. You see this solenoid here, these are the two things, then I connect them like this, make a circular thing, circular ring, and this then becomes a toroid. And because the field was near the axis of the solenoid, the field now is again along the axis of the toroid. The field is this, and then there are loops around this, and there are loops of current around this toroid. The field is along the axis of the toroid. The strongest field is along the axis of the toroid, and elsewhere it weakens, we shall see in a moment. So, to analyze this, we again take this structure. This is now a solenoid bent into a toroid, and these are the currents going in. You see, you have a loop like this, the current going in, the current coming out, the current going in, the current coming out. So, these crosses represent the currents going in, and the dots with circles represent the currents coming out. So, this is a flow of current in the toroid. So, to find the strength of the field, I take an Amperian loop within the toroid of radius capital R. Then what happens? Within this radius or within this circle of radius capital R, only the ingoing currents are included. Only the ingoing currents are included. The outgoing are not included. Therefore, once again, because of symmetry, the magnetic field must be along this loop. In fact, because it is a solenoid made into a toroid, it is always along the axis. So, it is along this, and the length or the when you integrate along the loop, then it is 2 pi capital R times the field strength along this circle, and that must be equal to mu 0 times the currents which are going in. So, 2 pi R B equal to mu 0 times n I, where n is the number of turns, and from this you get B is equal to mu 0 n I by 2 pi R, and n by 2 pi R is nothing, number of turns per unit length. Therefore, it is simply the same formula, mu 0 small n times I, where small n is the number of turns per unit length. And we note also that the magnetic field decreases as R, that is, from the center if I start, then its maximum it decreases with R, that is, as R increases from here to here, the magnetic field decreases, and it is strongest in along the axis. This expression, however, conceals the fact that the field inside the torus decreases with the increase of r. So, we must stick to the expression this. Instead of using this expression, it is much better to use this expression. To find the strength of the magnetic field outside the toroid, that is simple. Outside the toroid, you draw a circle of radius r, but this includes now the ingoing as well as outgoing currents, and therefore, the net current through this outside loop is 0. Therefore, the field outside the toroid will be 0. So, the net current through the loop is 0. Therefore, according to Ampere's law, B times whatever is equal to 0. Therefore, B is equal to 0. Similar arguments show that inside the hollow of this ring there is no magnetic field. This we have already done. In fact, inside the hollow also there is no current, and therefore, the field there is also 0. So, in the hollow it is 0, it decreases at r, and then it becomes 0 at the surface. That is the kind of field that the toroid has. Now, why is toroid so important? Scientists discovered that it is possible to reproduce in the laboratory the process of nuclear fusion of light nuclei. It is this process that is the source of energy in the sun and other stars. If it could be accomplished in the laboratory on the earth, we will have a source of clean energy, huge source of energy which is clean, and the best candidates so far that might react the light nuclei are deuterium and tritium, and if they react, then we can get lot of energy, and this energy would be clean energy. Deuterium 1 proton 1 neutron, tritium 1 proton 2 neutrons, and they must react in a certain region of space, and they give rise to helium and a neutron and lot of energy. In one such reaction you get 17.6 mega electron volts. But what is the problem? The problem is why this has not been achieved so far. See, the nuclei must be heated to a temperature of about 10 to the power 8 degrees to make them overcome the mutual Coulomb barrier between them. You see, these are nuclei, and there is lot of electrical repulsion between them, and to overcome the repulsion we must make them with very fast, so that they can collide, overcoming the repulsion. For that they have to be heated to a temperature of 10 to the power 8 degrees K, and when they react like that, it is called thermonuclear fusion. The heated nuclei, the plasma, they must be confined to a space, so that and given time to react, and the temperature is so high that if this plasma touches the walls, then the walls are destroyed. So, what is the solution? The solution is a toroid. So, we have a toroid which contains this plasma because of its magnetic field, and gives time for the reactants to react and give us energy. So far, of course, we have not succeeded, but there is every hope that in future we shall have this clean source of energy. We have seen that a toroidal device can be a very suitable thing for confining plasma, so that deuterium and tritium can react, and most laboratories in the world which are working in this area, they have built toroids, and one of the most well known toroidal device is called a tokamak, and this tokamak is found in all major laboratories around the world, and they are trying to achieve the thermonuclear fusion using these tokamaks. And this picture I have taken from Wikipedia. This is a familiar device, toroidal device called a tokamak, which is found in many laboratories around the world. So, in this lecture we have concentrated on Ampere's law, and we have found field due to solenoid and then due to a toroid, and we have also discussed the importance of toroids. In the next lecture, I intend to continue finding the magnetic field due to currents, but instead of Ampere's law, which requires some kind of a symmetry, we shall use a law which does not require symmetry. That law is called Biot-Savart's law. In the last lecture, we were dealing with Ampere's law. We also applied Ampere's law to a few systems. You must have learnt that it is easy to employ Ampere's law if the system has some kind of symmetry. For example, the system could be spherically symmetric or would have cylindrical symmetry or maybe longitudinal symmetry. If the system has any of these symmetries, then it is easy to apply Ampere's law. But most systems do not have any symmetry. So, what do we do? In that situation, we apply a law which is called Biot-Savart's law. This is applicable to any system without any problem. There is no symmetry required. And before we begin with Biot-Savart's law, let us recall Ampere's law. The Ampere's law, as you have seen in the last lecture, is the line integral of B dot d l is equal to mu 0 times the enclosed currents within the surface spanned by this loop C. Very quickly, let us apply this Ampere's law just to fix ideas. This figure shows a magnetic field pointing in the x direction. This is the x direction, this is the y direction. So, it is pointing in the x direction, but is not uniform along the y direction. You can see the field lines are not uniformly spaced. At the top and bottom of the loop, the magnetic field strengths are B 2 and B 1. So, we have a loop here and which is described clockwise, and the strength here is B 2, strength here is B 1, and its this side is equal to B. What is the current that flows through the area encircled by the loop? What is the current in this area? Let us see. The only contribution to the integral B dot d l comes from the sides of length L. This side is length L, this side is length B. See, this is perpendicular to the magnetic field, therefore, B dot d l is 0. This is also perpendicular to the magnetic field. So, B dot d l is 0. So, only contribution comes from this side and this side, both of which have length L. Since we are describing the loop clockwise, we have L times B 2 minus B 1 is equal to mu 0 I, where I is the current that we are seeking. So, I is given by L B 2 minus B 1 by mu 0, and this I is a positive quantity. So, therefore, considering that the loop is clockwise, we have to find what the positive current would be according to this loop, and you see the positive current will be out of the plane, coming out of the plane. If B 2 is less than B 1, then I becomes negative and the current would be going inside the plane. Historically, Biot-Savart's law was discovered about a decade before the Ampere's law. Both these laws give the magnetic field near steady currents, and both give the same result, and therefore, they must be equivalent. Moreover, the magnetic field due to a system of currents derived using both these laws give identical results. So, it must be remembered that Ampere's law is the analog of Gauss' law in electrostatics. I hope you remember Gauss' law. The integral of E dot d s is equal to q by epsilon 0, where q is the charge within the surface S. Incidentally, what would be the form of Gauss' law for magnetism? We have seen Gauss' law for electrostatics. What would be the form of Gauss' law for magnetism? It will be integral of B dot d s is equal to 0. Why 0? Because monopoles do not exist. We have seen that each magnet must have two poles. A single pole does not exist. Therefore, no surface can be found which encloses two kinds of poles which are not equal in strength. So, therefore, the right hand side is 0 and B dot d s is equal to 0. That means, the number of lines of force entering a surface is equal to the number of lines of force leaving the surface. It also means that magnetic field lines form closed loops which have no beginning and no end. You see, remember last time I showed you the field due to a bar magnet, and we had lines inside the bar magnet also, because we must form complete loops. Recall from the last lecture that when we use Ampere's law, we have to have a loop which encloses the currents. Biot-Savart's law is more general. It does not need any symmetry, it does not need any other thing, any loop, etc. But the Biot-Savart's law is in a differential form. Let us take a charge, positive charge q moving with velocity v, and we want to find the field at a point distance r from this charge. R cap is the unit vector in the direction of r. Then the field is given by mu 0 by 4 pi q v cross r cap by r square. You could have q v vector crossed r vector by r cube also. Some books will do that, but here we have q v vector cross r cap, which is a unit vector along r. Now, q v is I dt v and dt v is dl. Therefore, this form can be now put in this form: dB, the magnetic field at a distance r from the current element dl, where the current is in this direction, is given by mu 0 by 4 pi into I is the current, dl cross r cap is the unit vector in the direction of r, divided by r square. This is Biot-Savart's law. As before, the direction of the magnetic field is given by the cross product of dl and r cap, and you know how to get the product using the right hand screw rule. So, I will go from dl to r like this, and you can see if I go like this, then I am taking the screw out. So, the magnetic field at P would be coming out of the plane. Let us notice the resemblance between the Biot-Savart's law and the Coulomb's law. Both are inverse square laws. The magnetic field due to a current element decreases in much the same way as the electric field decreases from the source charge. These two laws also show that while static charges give us electrostatic fields, moving charges or currents give us magnetic fields. That means, there is a very intimate relationship between electric field and magnetic field. Clerk Maxwell recognized this intimate relationship. The two fields are now known as the two facets of the same entity, called the electromagnetic field. Now, electromagnetic field can be magnetic field or can be electrostatic field. Having learned the rule to find the direction of the magnetic field, let us focus on the magnitude of the field. dB is given by mu 0 by 4 pi, dl cross r cap can now be written as I dl sin theta by r squared, where theta of course is the angle between the current element and r. So, let us apply it so that the idea gets fixed. So, what we do, we take a very long current, in fact infinite long current, and find the field due to this current at the point P, which is a distance r, perpendicular distance r from the current. So, we make this structure, we have a small element dl and the distance capital R to P from dl, and this distance is L and this distance is r. So, we use now the Biot-Savart's law and find the magnetic field. So, using whatever I have explained, dB is given by mu 0 by 4 pi I dl sin theta r squared. Remember that the wire is infinitely long. Therefore, B is equal to mu 0 I by 4 pi, and therefore, I have to integrate now over dl, and this integration will be from minus infinity to plus infinity, because the wire is infinitely long, and because of symmetry I can, instead of taking limits from minus infinity to infinity, will take from 0 to infinity and multiply the result by 2. So, B is therefore given by 2 mu 0 I by 4 pi integral from 0 to infinity dl sin theta by r squared. I have the same figure again, and now we shall put sin theta in terms of r and r, and we will also put r by l in terms of the angle, and then take dl. That is how you do change the variable in integral problem. So, that is what we have done here, and now if we do all that, this integral 2 mu 0 I by 4 pi 0 to infinity sin theta cubed by r squared dl, this now reduces to 2 mu 0 I by 4 pi r integral from pi by 2 to 0 minus sin theta d theta. You see, when you change the variable on which integration is to be taken, you also have to change the limits. So, we have done that. This is little mathematics which you can do, there is no problem. Carrying out the integration now, the integral of minus sin theta is cos theta. So, and from pi by 2 to 0. So, we get this result b is equal to mu 0 I by 2 pi r. If you remember, you got the same result from Ampere's law, but there the process was much easier because we made use of symmetry. Here we did not make use of symmetry. Let us modify the same problem. Now, we have a wire which is of length 2L, that is from minus L to L. Earlier we had a wire which was from minus infinity to plus infinity, that is the difference. The rest remains the same. Therefore, we get the expression b equal to mu 0 I by 4 pi integral from minus L to L dl sin theta by r squared. Again, we shall use trigonometry and we get the result. First of all, we put sin theta equal to r by r, and r itself is r squared plus L squared. So, we do all that and we get b equal to mu 0 I r by 4 pi integral from minus L to L dl by L square plus r squared raised to power 3 by 2. And now, you can use the substitution L equal to r tan theta and integrate, and what you get is this result, b is equal to mu 0 I r by 4 pi into the quantity within brackets, which is 2 L by r squared into L squared plus r squared raised to power half. Again, we used some trigonometry and some results from integration, which I hope you are able to do. And the last equation can be written as b equal to mu 0 I by 2 pi r. You see, remember mu 0 I by 2 pi r was the field for infinite wire. So, we are writing this in this form. So, 1 by 1 plus r square by L square raised to power half, because we want to verify the earlier result. So, if we make L infinity, then this term vanishes and we get the earlier result. This is the way scientists or physicists go ahead. You must verify the results that you already know. Then you know that the extension or the work that you are doing is in the right direction. So, we get the same result that we got earlier. Let us take another example. The magnetic field at a point P on the line perpendicular to a straight current, that is, let me show you the geometry. Now, we do not have from minus L to L, we have just one line wire, and this point is not necessarily the middle point, and this angle is theta 1, this angle is theta 2, this is the current element, and this distance is r, these angles are phi 1, phi 2, and this is the point P at which we want to find the magnetic field. You see, in the last problem here, we did not find the direction, because now I have told you that the direction is given by the right hand screw rule. So, you can apply the screw rule and find the direction of the magnetic field. So, once again we have the same thing using a little trigonometry again. So, b is equal to mu 0 by 4 pi into I integral now from theta 2 to theta 1 of minus sin theta d theta. So, we integrate and we get this result. Instead of thetas, you can use phi's and you will get this result. In fact, this result is more often used, although it is equivalent to that, mu 0 I by 4 pi into sin phi 1 plus sin phi 2, where phi 1 phi 2 are these angles. So, we are not restricted to a long wire, we can have a short wire and we can find the magnetic field due to this wire at any point P on a line which is perpendicular to this. It is easy to see that for semi-infinite wire, again let us find out the result for semi-infinite wire. Semi-infinite wire is which goes from 0 to infinity, and for semi-infinite wire what happens that this phi 1 goes to pi by 2. You see semi-infinite wire in this direction, this angle goes on increasing till it becomes pi by 2, and this angle becomes 0. So, therefore, we can substitute these values and we get the result mu 0 I by 4 pi r. Let us use these semi-infinite wires, this result immediately, so that our ideas get fixed. So, we have two semi-infinite wires B and A carrying the same current I, and we have a point P which is along this wire at a distance L from this junction. So, this current in A will not contribute because they are in the same direction, this and this they are in the same direction, the cross product is 0, only this wire B will contribute. And using the result earlier, we can semi-infinite wire the result that we used earlier, just we have to put the distance equal to L and we get the result B is equal to mu 0 I by 4 pi L. That is the magnetic field at this point. You can find the direction of the field, whether it is inside going into the plane or coming out of the plane, by applying the right hand screw rule. Let us apply this to a very simple problem. This problem I have seen in some competitive examinations, so I chose that problem. We have a square of side L, and this is the structure. We want to find the current is I in all branches, and we want to find the field at the center. So, these angles are 45, 45. So, apply this simple 45, 45, and the whole thing you can do easily, and you get B equal to mu 0 I, that result we apply, and side R in this case is L by 2. So, we substitute R equal to L by 2, phi 1 is 45 degrees, phi 2 is 45 degrees, find the signs and plug in, and you get the result. Let us now apply Biot-Savart's law to a circular current I going in this clockwise direction. It is very simple, because d l cross R is simply d l r, in this case r cap. So, therefore, just d l. So, the d b is mu 0 I by 4 pi r squared d l, and the integral over d l, because the I is constant, r is constant. So, simply integral over d l, and integral over d l is 2 pi r, is 2 pi r. So, integral d l becomes 2 pi r, and therefore, the result is B equal to mu 0 I by 2 r. You remember this result again we got using Ampere's law. So, once again we verify the same result. If there are n tightly packed loops, each loop or turn contributes to its own field. Therefore, the field due to n turns of the coil is mu 0 I n by 2 r. Mu 0 I, multiply that by the number of turns, and therefore, mu 0 I n by 2 r. Now, if wire is only half circular, then the integral over d l would be simply pi r. So, you will get the result. If the wire encloses an angle phi, remember phi in this case must be taken in radians. For example, 60 degrees is pi by 3 radians, 90 degrees is pi by 2 radians. So, we must express phi in terms of radians, and then this simply is phi times r. So, the result, therefore, the magnetic field at the center is mu 0 I by 4 pi r into phi, because phi r is the integral of d l. Let us apply this to this problem. We have these two quadrants, and the current is flowing like this. Immediately this one and this one would not contribute, because the cross product of d l with r would be 0 at P. So, therefore, they do not contribute. Only this quadrant and this quadrant they contribute, and we have already found the semicircle. So, quadrant is just half of that. So, the field would be the integral d l would be simply pi into radius by 2. For semicircle it was pi r, for a quadrant it is pi r by 2, and therefore, B becomes this. Now, for this radius is B, so it will be mu 0 I by 8 into 1 by B, and this radius is A. So, it will be mu 0 I by 8 into 1 by A. Now, why this minus sign? Because the field due to this is in one direction and field due to this is in the opposite direction. Therefore, the net field at P would be the difference of these two, and you can see by using the same right hand screw rule that the field net field is coming out of the plane. No, the lower arc gives a field which is going in. So, that is stronger because B is less than A. So, the field net field is going inside. Let us now calculate the magnetic field. This is very important. Magnetic field due to a loop of current of radius r at a point on its axis. We have found at the center of the loop, but on the axis now. So, the geometry is clear. We have a loop, we have a point at a distance x, and this distance is r. R cap is a unit vector shown in red, dl is the current element shown in green, and the current is going in the anticlockwise direction. That is all. And now, imagine a plane which contains dl and r cap. Now, in this plane, the angle between these two planes is this angle, which is pi by 2. This is the only problem, the only difficulty that comes in, and you have to remember that this is dli, this is dli, let us say, or like this, and this is r cap, and we are worried about this plane containing dl and r cap, this plane, and in this plane this angle between the two is pi by 2. Therefore, dl cross r cap simply becomes dl. If you have got this right, then you will not make any mistake. So, let me explain to you again. We have got dl, the current element, we have got r cap in this direction, and we have to look at the plane that contains this and this, that is this plane, and in that plane the angle between this and this is pi by 2. So, therefore, dl cross r cap is simply dl. The rest is just geometry. You see, now the field at the point x from the center of the loop would be given by this in this direction. Again, use dl cross r and you get in this plane, right, and this has two components, dbx and dby. Now, if I choose another current element here, then this dby would be in this direction and two dbys would cancel. So, diametrically opposite current elements would cancel the y component of the magnetic field. So, we have to worry only about the x component of the magnetic field, that is dB cos theta, and we know theta, therefore, we can use this. So, dBx would be mu 0, this result we have already obtained, mu 0 I by 4 pi r squared dl, and the x component would be cos theta, and cos theta can be put in terms of this radius. So, r squared plus x squared is r, the magnitude of this, and therefore, cos theta is r by r squared plus x squared raised to power 3 by 2, and substitute that. The integral then, integral over phi, integral over dl is then just 2 pi r, and substitute that. So, we get bx is equal to mu 0 I by 2 r squared by r squared plus x squared raised to power 3 by 2. That is the field at this point. The direction of the field, you see, dl cross r would be in this direction as shown, and along the axis the component would be cos theta of that. So, that is the magnetic field along the axis of the loop. And you can easily see that if I put x equal to 0, we get the center of the loop and we get the earlier result. This is r cubed and this is r square. So, we will be left with 1 r. So, it will be mu 0 I by 2 r, the earlier result, and therefore, once again we verify that what we are doing is the right thing. And now, I just show you the plot of this magnetic field. I plot B by B 0, B 0 is the field at the center at x equal to 0. So, we plot the field and you see the field goes like this. It is maximum at the center and then decreases. You see, if I loop, there is a maximum at the center and then decreases as we go along the axis. And if there are n turns of the coil, you see solenoid which we were discussing last time, then the field becomes mu 0 n into I by 2 r, because each turn of the coil contributes to the magnetic field. In this lecture, you see we have concentrated on Biot-Savart's law. First we discussed the Ampere's law, and then we are now discussing Biot-Savart's law. The difference between these two is that Biot-Savart's law is differential in nature, whereas Ampere's law is integral in nature. And to apply Ampere's law, we need certain symmetry in the system. Biot's law is more general. It does not require any symmetry or such considerations. It simply you just apply the mathematical expression and you get the magnetic field. The direction, of course, you get by applying the right hand screw rule. In the next lecture, we shall continue with this, and in fact, we shall study the motion of charges in electric field first and then electric and magnetic fields together. In the last lecture, we were discussing Biot-Savart's law, which allows us to find the field at any point due to a distribution of currents. This law is quite general and we applied it to many situations, and I hope that you learnt how to tackle problems which are based on Biot-Savart's law, and you are able to find the magnetic field at various points. Also, I emphasized all the time that the direction of the field can be found by the cross product d l cross r cap. So, you apply the right hand screw rule and you can find the direction of the magnetic field, the point that you are asked. In this lecture, I am going to consider now the motion of particles in electric fields and electric and magnetic fields. Let us start with electric field, and let us take a charged particle which has charge q. It is moving an electric field, and the force we have seen already on this charged particle is q e, and this force of course is a vector quantity. So, it will be in the direction of the electric field. So, having learnt that it is always going to be in the direction of the electric field, let us forget about the direction for the time being and concentrate on the magnitudes. Now, if F e is the force which is equal to q e, then the acceleration is q e by m, where m is the mass of the charged particle, and E itself is v by d, where v is the potential difference applied across a certain distance d. Now, we come back to mechanics. We use v equal to u plus a t to find out the velocity after a certain time t, when the particle starts with initial velocity 0. Similarly, s half g t square, you remember from the gravity. So, half a t square half q v by m d times t square, and in terms of the distance covered, we know v is equal to square root of 2 a s. So, we substitute the value of a and we get 2 q v s divided by m d and square root of that. The time required to travel the distance s is, again you can, from this equation we have got t square here. So, you can get t equal to m d s divided by q v under root. And the kinetic energy, once the particle has travelled through a potential v, then the the work done is q v, and therefore, the kinetic energy is half m v squared, which is q v, the distance travelled is s, and v by d is the field. Therefore, the kinetic energy is q v s by d. So, that is the kinetic energy, and remember that the kinetic energy here is depend on the charge and the electric field and the distance covered, but not on the mass. So, protons and electrons travelling through the same potential difference, the same distance between in the potential difference, they would have the same kinetic energy. So, the kinetic energy is half m v squared q v, and from this we get v equal to 2 q v by root of m, and this velocity is sometimes called impact velocity. And from this expression, or earlier one, if we put q equal to E and v equal to 1, then we get our unit electron volt. Electron volt, you remember, is the work done when electron moves through a potential difference equal to 1 volt. We have now electric field supplied by these two plates. The field is in this direction. The distance between the plates is d, and the length of the plates is L, and we have got x coordinate system, x in this direction, y in this direction. So, a charged particle comes here, and let us see what happens to this. And suppose the electron enters a field with velocity v x in the x direction, that is in this direction. Let us see what happens to it. Since there is no force in the x direction, the field is in the y direction. In the x direction there is no field, therefore, there is no force, and it continues with the velocity v x in the x direction. In the y direction, there is a field v by d, and with velocity v x, it covers this distance x in time x by v x, and in that time the distance travelled along the y axis because of the attraction of the electric field is, again using the expression we have derived earlier, half E v by m d into t square, and t square here is x square by v x squared. And in coordinate geometry, you must have read that this equation y equal to some constant times x square represents a parabola. So, this path is a parabola. This is the equation of a parabola. Thus, the path of a charged particle in an electric field perpendicular to its direction of motion is a parabola. And knowing y equal to half whatever this expression is, we can get E by m. You see, if we know v, d, x, v x, if we know all these things, we can get E by m. And this is the basis of Thomson's experiment for determination of E by m. So far, we had only electric field. Suppose magnetic field is also present, then we have seen that if magnetic field is present and a particle, charged particle of charge q is moving with velocity v in the field, then the force, magnetic force on this, which is called Lorentz force on this, is q v cross b, and its magnitude is q v b sin theta. Now, if electric field is also present, then the total force on the charged particle, we have seen this already earlier, is given by q E plus q into v cross b, that is q into within the bracket E plus v cross b. And you also, I think, need to be reminded that Lorentz force v cross b is perpendicular to both b and v, and is perpendicular to the plane containing b and v. B and v is this plane, the force is perpendicular to this plane. B and v is in this plane, and the force is perpendicular to that plane. So, This I think we have discussed earlier also, and you would remember. And again V cross B is given by the right hand screw rule. So, you can find the direction, we have done it several times. Now, let us take the case. A particle is moving in the along the x direction, the magnetic field is along the y direction. What happens to this? Now, V cross B is in the z direction. So, the particles turn to the right. Now, therefore, the direction of its velocity changes, the magnitude does not, because the force is perpendicular to both V and B. Therefore, there is no change in the magnitude of velocity, but there is a change in the direction of the velocity. Now, if I take a cross product between this V and the new V and B, I will find that there is more bending, and eventually if I keep on doing this, I will find that this particle goes in a circular path in a plane perpendicular to B. So, if I have a charged particle, if I have a perpendicular field B and charged particle coming, then this charged particle would go in a circle around this field as shown here. And you can find the direction. The positive charge will go in a clockwise direction and the negative charge would go in a anti-clockwise direction, if this is the direction of the B and this is the direction of V. All that you have to do is to find V cross B, and if it is negative charge, then give a negative direction to that. And this motion carried out by the charged particle in a magnetic field is called gyration. We say that the charged particle gyrates around the magnetic field lines. It is easy to see that a negative charge will gyrate in the opposite direction, and the frequency with which this gyrates is called the gyro frequency, or more popularly cyclotron frequency. Now, if an electric field E is also present in the same direction as the magnetic field, that is both B and E are in the same direction, then what happens? We have seen that B would make the particles go in a circular orbit around the magnetic field lines. E would pull them up, because E applies a force in the direction of the field. So, therefore, a charged particle which was going like this now starts making a spiral motion. So, if both B and E are present, and V is like this and B is like this and E is also like this, then a positive charged particle would go in a spiraling motion. When a charged particle encounters a magnetic field, it gyrates around it and cannot penetrate it. You see, a particle was moving like this, it found a magnetic field, then it got trapped, because it cannot go past the magnetic field. It is trapped in the magnetic field, it just goes around the magnetic field. Let me show you this. This is also a particle was coming, there is a magnetic field. So, it starts gyrating around the magnetic field lines and is trapped, it cannot go anywhere. So, that is what we are saying. We say that the charged particle is trapped in the magnetic field. The earth is surrounded by two regions populated by charged particles, mostly electrons and protons. These are called radiation belts or von Allen belts. I think those of you who are interested in space physics would have by this time learnt about these von Allen belts. They were discovered by the scientist von Allen, and he found that there are two regions surrounding the earth where there is a concentration of charged particles. These are known as two belts. How are they trapped? Let us see. This is the earth, this is the magnetic field line. A charged particle was coming here and it just got trapped and moving, it starts moving along the field line. It cannot penetrate the earth's magnetic field. Since the magnetic field of the earth is neither constant nor uniform, the motion of the trapped particle is quite complicated. I have shown it a simple picture, but that is not the case. It is a very complicated thing, because both magnetic field varies both in time and space. Many of the particles trapped in the radiation belts have high energies. They pose a grave threat to the safety of astronauts and spacecrafts. You see, you must have heard the expression space weather. Space weather includes the condition of these two belts. One space scientists therefore keep a careful watch on the variation of particle intensity in these belts, and they time their launches so that the effect on the satellites is minimum. Here this picture is from SSCL Montana University. Here are the two belts. This red one is called the inner belt, and this gray one is called the outer belt. So, we have two belts, the inner belt and the outer belt, and incidentally we also show the axis of rotation of the earth and the magnetic axis of the earth, just to familiarize you with this kind of thing. And here I show you a more complicated picture. What is happening is the particle trapped in the earth's magnetic field. It was coming, the poor fellow could not penetrate the magnetic field, and it got caught in the magnetic field and starts traveling along the magnetic field. As it goes, the magnetic field here becomes stronger, just the earth's field, earth's field is like this. So, it is stronger, the field lines are more crowded here than here. So, the field is stronger, and you will learn later, if you happen to learn plasma physics, that strong magnetic field here, this reflects the particles back, and the particle then keep on moving back and forth from here to here. These are called mirror points, because the reflection is like a mirror. So, these are called mirror points, and these are the places where the magnetic field is very strong, and we go like this. And two belts discovered by Van Allen are the inner belt and the outer belt. You can find more about these from the sources I have quoted here, and you can find what happens to these belts and what is space weather and so on, and why scientists, when they launch satellites, are worried about the activity in these belts. These belts of charged particles can harm these spacecrafts or astronauts, but they also are very good in a certain way. And what is that? If the energetic particles which are trapped in the magnetic field, they could reach the earth, they have very high energies, and therefore, they could endanger the human life on the earth. By trapping these particles, therefore, the magnetic field acts as a protective shield, just like the shield which protects us from the harmful effects of ozone, and this shield is called magnetic shield. This allows life to develop on the earth. If magnetic shield were not there, the particles, very high energy particles, would simply come and hit whatever life is there on the earth, and they would destroy that. So, this magnetic shield is very important for us, because it has allowed the life to develop on the earth. This is quite similar to the shield provided by the ozone layer in the atmosphere, which protects life on the earth from the harmful effects of the solar UV radiation. This you know, but perhaps you did not know that magnetic field also serves a very important purpose of preventing the high energy particles from coming and hitting us. Let us take a small example. The velocity of the particle is like this, magnetic field is like this. This I have done just to familiarize you with the various kind of situations that the examiners can pose before you. So, V is like this, B is like this. So, what you do is V cross B. So, you take the magnetic field here, this is the velocity, this is the magnetic field. So, V cross B, and that would give you the direction of the field. Similarly, here say a particle is coming with velocity V, and then it finds a magnetic field B. So, what do? We break the velocity into two components. One component parallel to B is not affected. The component parallel to B would trap the particles in the gyrating motion around the field lines, and therefore, the result would be this. The parallel component would carry the particle forward along the magnetic field, and the perpendicular component would gyrate, make the particles gyrate, and the two together make the particles move in a spiral around the magnetic field lines. Now, a charged particle is moving in a circular orbit with uniform speed v. It produces a magnetic field B at the center of the circle. Find the radius of the circle. We have found already the magnetic field due to a loop, and a charge q moving in a circular orbit is equivalent to a current, right, and this current is q v by 2 pi r, and now just apply this formula mu 0 I by 2 r, that is equal to B, and from this you can get r. R is mu 0 q by 4 pi into V by B and square root of that. Simple application, not much. All that you have to remember is that a moving charged particle is equivalent to a current, and if it is going in a loop, then the current is equal to q v by 2 pi r. This 2 pi r by v is actually the time taken. So, q by t is the current. Now, again all that you find the magnetic force acting on a charged particle. So, V cross B, V is given and B is given. B is 2 Tesla in the y direction, and V is given by 2 I cap plus 3 j cap in terms of 10 to the power 6 meter per second. So, you just take the cross multiplication. You know that I cross I is 0, I cross j is k. So, this cross product would give you a vector k in the direction of k, but because of the negative sign, it would be in the direction of minus z, not in the direction of z. Under the influence of a uniform magnetic field, a charged particle is moving in a circle of radius r with constant speed v. Find the time period of the motion. It is easy. All that you do is equate the magnetic force with the centripetal force, because magnetic force provides the necessary centripetal force for the motion of the charged particle in a circle. From this you get the velocity, from which you get the time period, and the time period is 2 pi m by b q. The reciprocal of this time period would be the gyro frequency or cyclotron frequency, and this is independent of both v and r. The frequency or the time period, they are independent of both v and r. It depends only on the mass of the particle, charge of the particle, and the magnetic field. The frequency, the cyclotron frequency is given by 1 by t, which is q v by 2 pi m. So, notice that the radius of the circular orbit r is m v by b q. It depends on the mass of the particle. So, if I know v, b and q, I can get the mass of the particle. So, by keeping v constant, q constant, and varying b, I can separate particles of different masses. This is the principle of the mass filter or the mass spectrograph. You can, in a beam there are particles of various masses. So, by adjusting they are moving with, let us say, the constant velocity v, and the charge also let us say is the same, then by varying b or within the b they would have circles of different radii, and so you can separate the particles. Magnetic field acts as a mass selector. Now, suppose there is a crossed field, that is, you have magnetic field going inside and the electric field from positive to negative in this direction, and there is an electron, poor electron here. What will happen? You can work out, electron would be attracted to the positive terminal. So, it will travel like this in this parabola. The given magnetic field would make it move downwards in a parabola, and the deflection on the two sides would be the same, and therefore, the charge can go without any deflection. The electric field is vertically downwards, while the magnetic field is going into the plane. The electric field deflects the particle upwards, the magnetic field deflects it downwards. The two deflections are equal. That means, E E is equal to E V B. The electron of velocity v will continue undeflected. That means, if I adjust T and B, I can, out of a beam, I can select a certain velocity. This arrangement is called velocity selector, and this v would be E by B from these expressions. Now, let me repeat something that we did earlier. I have now a long wire, very long wire, and I make a loop of this as shown here. So, I make a loop of this wire. So, in the loop the current is going anticlockwise, and in the wire it is going in this direction. So, I want to find out the field at the center of the loop. Since we know both the expressions due to a loop and due to a long current, we can just add them or subtract if the fields are in the opposite direction. In this case, you can work out, I leave it for you as an exercise, that the fields are in the same direction, the field due to this loop and the field due to this wire at the point which is at the center of the loop, they are in the same direction. So, you just add them. So, we get B, the magnitude of B is B loop plus B wire, which is mu 0 I by 2 pi r, the formula we derived earlier, plus mu 0 I by 2 pi r, again the formula derived earlier, and we sum them together. And this is the magnitude of the field due to this arrangement. Let us modify the arrangement slightly. Now, I take the wire and make a loop like this, not like this, but this kind of sigma, Greek letter sigma. So, the current goes like this and takes a loop and then goes like this. Again we have to find the field at the center of the loop. Now, you can work out and you will see that the fields now are in the opposite direction, and therefore, you must take the difference of the two fields. The field due to the loop is mu 0 I by 2 r, and field due to the long wire is mu 0 I by 2 pi r, and since this is weaker field and this is in the opposite direction to the field of the loop, therefore, the ultimate expression is mu 0 I by 2 pi r into 1 minus 1 by pi, and that is this field is okay, you can work out going into the plane. So, these are simple examples, simple exercises, there is no problem. I wanted to familiarize you with these problems, because these are favorites of examiners. So, in this lecture we discussed the motion of charged particles in electric and magnetic fields, and we saw that the particle moving with velocity v in a field which is perpendicular to its direction of motion gets caught and starts gyrating around this. If there is also electric field present in the direction of the magnetic field, then it has a spiraling motion, it goes up, but keeps on spiraling, keeps on gyrating. In the next lecture, I intend to start with magnetism. So, we shall start in the next lecture with magnetism, and then we shall study the magnetic properties of materials and so on.
Hello viewers, and welcome to our series on 3-dimension geometry. Today we will discuss the shortest distance between two lines. Now, if you think of two lines which are intersecting, then the shortest distance is always 0. If two lines are parallel to each other, then the distance which is the shortest distance is the perpendicular distance of a point on one line to the other. So, is there another possibility? We are talking about 3 dimension. We are talking about lines in space, and therefore, there is always a possibility that the two lines are neither intersecting nor parallel. Such lines are called skew lines, and we are interested in learning how to find the shortest distance between such lines. Let us take a look at what skew line means. We define two lines to be skew lines if they are non-parallel and non-intersecting. Now, suppose we look at again the room where you are sitting. Can you identify two lines which are skew, lines which are neither parallel nor intersecting? If you look at the edges of these walls which are in the same color, then these lines will be neither parallel nor intersecting, and therefore, they are the skew lines. Another example in this illustration, if I take a line which is along the railing of the balcony and I take a line along the stick which is lying inclined to the floor resting against a particular wall, then these two lines will also be skew lines. We are interested in finding the line of shortest distance and then the shortest distance. If I have two lines which are skew lines, so use your spatial skills to visualize these lines L1 and L2 as neither parallel nor intersecting, and if you can think of a line which is perpendicular to both L1 and L2, then such a line is called as the line of shortest distance, and the distance PQ which is intercepted by the line L1 and L2 on this line of shortest distance is called the shortest distance between the skew lines. We are looking at a relation between two given lines whose vector equations or later Cartesian equations may be given. How do we find the distance which is the shortest distance between these two skew lines? So, start with, if I take the figure and take the point S and T to be the points which are given with the position vector A1 and A2 and PQ to be the shortest distance, then the projection of ST along the vector which is defining the line of shortest distance will give me the shortest distance. So, the projection of ST is what I am interested in calculating, and for that we first determine what is the vector PQ. Now, vector PQ is a vector which is perpendicular to both L1 and L2. In magnitude, it is say d units, the magnitude of shortest distance which we are in search for. The direction of PQ will be same as the vector n cap, which is known to be perpendicular to both B1 and B2 vector which are defining the two lines. And we know that the cross product of B1 and B2 gives us the direction which is perpendicular to both the vectors B1 and B2. Therefore, the unit vector n cap will be B1 cross B2 divided by magnitude of B1 cross B2. Vector algebra also taught us that if theta is the angle between the vector ST and vector PQ, then the projection, that is PQ distance, will be same as ST cos theta. Cos theta using the dot product comes out to be same as d n cap dot A2 minus A1 upon d times the distance ST. We know that n cap is B1 cross B2 by magnitude B1 cross B2. So, if I replace that here, I know how much is cos theta. Therefore, the shortest distance which was given the symbol d is PQ defined as a projection ST cos theta. So, if you multiply the above quantity with ST, you get an absolute value of B1 cross B2 dot A2 minus A1 upon B1 cross B2. The absolute sign is considered because the direction of B1 and B2 is not known to us. So, you may end up with a negative quantity there in the numerator, and that is the formula that we will now be practicing with our next two questions. You also must note that this is one of the very important formula result which is very often tested by CBSE as well. So, you need to be little ready with it. At the same time, it is an easier relation to know once you have done a practice or two. Let us see what the question says. Find the shortest distance between the lines whose equations are vector r is equal to I cap plus 2 j cap plus 3 k cap plus lambda times I cap minus 3 j cap plus 2 k cap, and the second equation is r vector is equal to 4 I cap plus 5 j cap plus 6 k cap plus mu times 2 I cap plus 3 j cap plus k cap. So, if I relate these two equations with the general form that we had, then I know that the vector A1 and A2 are the coordinates of the point that are lying on the line. In this case, the vector A1 is I cap plus 2j cap plus 3k cap. Vector B1 is the vector which defines the direction. So, that is coming as the vector in the equation which is multiplied with lambda. So, that is I cap minus 3j cap plus 2k cap. Similarly, we know vector A2 and vector B2. What I need in the formula is B1 cross B2, I need A2 minus A1 vector, I need the dot product of these two, and I need the magnitude of B1 cross B2. So, it is a very simple straightforward calculation, all based on what you must have learned in the vector chapter. So, if I find what is A2 minus A1, I would get 3I cap plus 3j cap plus 3k cap. B1 vector cross B2 vector is nothing but the calculation of the determinant, where the first row is I cap, j cap, k cap, and then you write the components of the vector B1 in the second row, vectors B2 components goes in the third row. Expand the determinant very carefully, an error here can affect the entire calculation. Once you have B1 cross B2, then we find the magnitude of B1 cross B2, which in this case is simplified root of 171, same as 3 times root 19. So, I think now we are ready to look at what we want. We just need A2 minus A1 dot B1 cross B2. If you find the dot product, it turns out to be 9 in this case, right. We are multiplying the components of A2 minus A1 and B1 cross B2 correspondingly. So, I get minus 9 into 3 plus 3 into 3 plus 9 into 3 results as 9. So, what you have to now do is just plug in the values of each of these in the formula, and the shortest distance comes out to be 3 by square root of 19 units. Given an equation in vector form, it was easier to use the formula because everything is easily related. Of course, the same formula can be translated into Cartesians, but it becomes a bit cumbersome. So, I will advise you to look at a Cartesian equation of a line and get the required information by translating the Cartesian into the vector equation, and then use the formula of shortest distance as we have done in our earlier question. So, suppose now I show you an example of equations given in Cartesian form, and we have to find the shortest distance between them. The question here has two lines given as x minus 4 by 1 equal to y plus 1 by 2 equal to z by negative 3, and the second line is x minus 1 by 2 y plus 1 by 4 equal to z minus 2 by negative 5. So, what you all have to do is translate these equations into the vector form. So, we know the known point on the first line was 4, negative 1, 0, and therefore, our vector is equal to 4 I cap minus j cap plus lambda times. Direction ratios of the first line are 1, 2 and negative 3. So, it will become I cap plus 2j cap minus 3k cap, and therefore, the same way second equation translates as r vector is equal to I cap minus j cap plus 2k cap plus lambda times 2I cap plus 4j cap minus 5k cap. And now, we are ready to find what is A1, B1, A2, B2 all as required. These vectors can be identified without writing the vector equations as well. So, if you are confident of doing that, go ahead and simplify as required. So, we are ready to find what is A2 minus A1, B1 cross B2, need the magnitude of B1 cross B2, need the dot product of A2 minus A1 with B1 cross B2, and plug in the values in the shortest distance formula. That gives us, in this case, as you can see, the numerator turns out to be negative 6. That happens because of the orientation of B1 cross B2. Therefore, the absolute value sign is important, and it gives us the shortest distance to be same as 6 by root 5 units. Now, we did say that distance between two parallel lines can always be calculated using the point on one of the line and then finding the perpendicular distance of that point from the other line. We did demonstrate this in our previous lesson as well. But can I use what we have just discussed right now in the same manner and see what the shortest distance between two parallel lines be and get a formula which is easy to use? Yes, you can. So, let us just look at the result. If I take two lines which are parallel to each other, then their equations will look like vector r is equal to vector a1 plus lambda times vector b, and r is equal to vector a2 plus mu times vector b. Note that you have the same vector b in both the equations, and therefore, if I take these two lines now, they are now parallel to the same vector b. S and T are the points with position vectors vector a1 and vector a2. So, if I draw perpendicular from T, then the distance Tp is the required one. Now, this distance Tp can be calculated using again the vector algebra, where we learned that if I take B cross vector St, the B is a vector which is along which the lines are defined, then B cross vector St is magnitude of B, magnitude of St, sine theta into a unit vector n cap, which is in the plane of the lines L1 and L2. Now, this vector St is known to us as vector a2 minus vector a1. Using just trigonometry in the triangle SPT, the distance PT is nothing but St sine theta. So, I need to now use this, and replacing in the relation B cross vector St, I get B cross a2 minus a1 is equal to magnitude of the vector B into Pt, because vector St, magnitude of vector St is same as distance St. So, St sine theta gets replaced by the distance Pt times the unit vector. So, if I just equate the magnitude of the two sides, I will get magnitude of B cross a2 minus a1 to be same as magnitude of the vector B into distance Pt, and therefore, the shortest distance, which was Pt distance, becomes same as the magnitude of B cross a2 minus a1 divided by magnitude of the vector B. So, if I have the two lines given to us which are in the same direction, so I know the vector B, I know the vector a1 and a2, I can take this formula as a result to find the shortest distance between those two parallel lines. I hope today's lesson has made the task of finding shortest distance between skew lines a bit easier for you. Do take up a few more questions and make sure that you get the hang of it. All the best to all of you. Hello and welcome to our series on 3-dimension geometry. In our previous lessons, we talked about line in space. Today, we will discuss equations of plane. Plane, as the literal meaning of the word goes, suggests something which is smooth, and that is how we define plane in more technical language as well. We say that a plane is nothing but a flat surface on which a straight line joining any 2 points on it would wholly lie. and we are looking at finding the equations of the plane which will be uniquely determined if any one of the following is known. The first one is if I know the normal to the plane and its distance from the origin. Now, normal to the plane is nothing but a direction, in our language a vector, which is perpendicular to the plane. So, if I know the normal and I know the distance of the origin from the plane, then we are looking at a possibility of finding the equation of the plane. The other possibility would be if I know a point on the plane and the normal to the plane. Third possibility would be if I know 3 non-collinear points through which the plane passes. Now, each of these would give rise to the equation of the plane that we are getting ready to learn. Starting off with the first one, equation of plane in normal form. When we are given the perpendicular distance of origin from plane, say the distance d, and we are given a normal vector. So, we know the vector which is perpendicular to the plane. So, if I take O n to be the perpendicular from origin to the plane, then the distance O n is small d and the vector O n is in the same direction as the vector n that is given to us. Therefore, vector O n will be d times the unit vector along the direction of the vector n. If I take P to be any point on this plane with position vector vector r, then I know that the vector O n, which is perpendicular to the plane, will also be perpendicular to the vector n p that is contained in the plane. And therefore, the dot product condition, that is the dot product of these two vectors equal to 0 must be satisfied. So, you do get d n cap dot r vector minus d n cap equal to 0. As we simplify this, I get r dot n cap equal to d, and this is what is known as the vector equation of plane in normal form. Also, as I rewrite this using the vector r as x I cap plus y j cap plus z k cap and n cap as l I cap plus m j cap plus n k cap, where l m n are direction cosines of vector n cap. N cap, remember, is a unit vector. This gets rewritten as l x plus m y plus n z equal to d. So, that becomes the Cartesian equation of plane in normal form. Now, what we have to note here is that if the two equations, that is r dot n cap equal to d, had an unit vector, and in place of a unit vector I have, say, a vector n known to us, and we have an equation given as r dot vector n equal to d, then the Cartesian equation of the plane would translate as a x plus b y plus c z equal to d. Then a, b, c, that is the coefficients of x, y, z, are the direction ratios of the normal to the plane. Another possibility is if I know the point through which the plane passes and I know a vector which is perpendicular to the plane. The normal form depends on knowing the distance of origin from the plane, which is not always available. So, this form, that is where I have a point given and a normal, is going to be most frequently used form. So, how does it affect the equation of the plane? Starting with, if I look at the figure, then I know the position vector of the point A, say the vector A with coordinates x 1, y 1, z 1 known. I know the normal to the plane. So, vector n, in this case symbolically represented here as touching the plane, is not necessarily to be there. It is just a direction which is perpendicular to the plane that is known to us. So, that vector n has direction ratios as a, b and c. If I take p to be any point on this plane whose locus has to be formed, then we know that the vector AP is perpendicular to the normal, that is the vector n. So, the dot product of vector AP and vector n must be 0. So, vector r minus vector a dot vector n must be equal to 0, and that gives rise to what is known as the vector equation of the plane. You may simplify this further and write as vector r dot vector n equal to vector a dot n, but it is perfectly fine to look at it like this as well. Rewriting this in Cartesians, it will turn out to be same as a times x minus x1 plus b times y minus y1 plus c times z minus z1 equal to 0. And therefore, that becomes the Cartesian equation of plane passing through the point x1, y1, z1, having normal with direction ratios a, b and c. If we revisit the two things that we have discussed so far, vector form of equation of the plane is given as vector r dot vector n equal to d. Now, vector n is a normal to the plane and d is that quantity that would simplify if you find vector a dot vector n. In Cartesian, after simplification, the equation of the plane in general will always simplify down to a linear equation in x, y and z in the form ax plus by plus cz plus d equal to 0. I have chosen capital D with an understanding of taking it a little different from the d earlier. Otherwise, any constants a, b, c and d as in that sense will be the required, and a, b, c, that is the coefficients of x, y and z will define the direction ratios of the normal to the plane. I think we are now ready to look at the third possibility. What if I have 3 points, non-collinear points through which the plane is passing? Instead of giving you a general formula for that, let us just take a question where you have to form equation of the plane which is passing through 3 non-collinear points, and let us see what the method is and what kind of a equation I get at the end of it. The problem here states that find the vector and Cartesian equation of the plane passing through the points A with coordinates 1, -2, 5, B 0, -5, -1, C -3, 5 and 0. Now, if we try to make a picture as shown here, things will become easier to follow. If you take 3 points on the plane, say as marked here A, B and C, then we know, since by the definition and the characteristic of the plane, the vector AB and the vector AC will completely lie on this plane. And so, the direction which is the normal, which is much required to find equation of the plane, the direction of the normal will always be perpendicular to the vector AB and the vector AC both. That is what will work as a key result and a concept. Let us begin with taking that vector n to be parallel to the cross product of vector AB and vector AC. Since vector algebra taught you that cross product of any two vector is always parallel to the given two vectors, and therefore, if I find the vector AB as position vector of point B minus position vector of point A, find position vector of C minus position vector of A to get vector AC, then find the cross product using determinant, I get the vector AB cross vector AC to be 57 times I cap plus 19 j cap minus 19 k cap. So, normal is any direction which is perpendicular to the plane containing these 3 points, and therefore, normal will be same as the vector AB cross AC. We did see that equation of a plane through a point is given as vector r minus vector a dot n. Now, vector n gets replaced with AB cross AC. So, we have everything ready to form equation of the plane, and that simplifies to be same as vector r dot 57I plus 19j minus 19k cap equal to negative 76. Simplification of vector A and the vector n, which is along AB cross AC dot product, and therefore, simplification gives us the final answer as vector r dot 3I plus j cap minus k cap equal to negative 4 as the required equation. To rewrite this in the Cartesian form, all you have to do is replace vector r with xi cap plus yj cap plus zk cap, and the dot product will give me 3x plus y minus z equal to negative 4, which I can rewrite and simplify as 3x plus y minus z plus 4 equal to 0, and that is the required Cartesian equation of the plane. So, the three forms that we discussed today, one starting with the normal form, where we need the distance of origin from the plane, another form where we had a point known and direction which is normal to the plane, third case where we had 3 points known, non-collinear points. Now, suppose these 3 non-collinear points were special points, special as in terms of they are nothing but coming out as points where the plane touches the 3 axes. That is what comes out as the intercept form of the equation of plane. Let us take a look at how and what special form does it result in. Here we have a plane making intercepts A, B and C units on x, y and z axis respectively. So, the plane must meet the 3 axes at the point A00, 0B0 and 00C respectively. Now, in this case again you can use the same procedure as in our previous question, because these are 3 non-collinear points. But just to get that special form, if I take Cartesian equation of plane as Ax plus By plus Cz plus D equal to 0, then I know that A comma 0 comma 0 lies on this plane. So, if I replace x, y, z with these coordinates, I get a condition which tells me that capital A is equal to negative d upon small a. Similarly, you get capital B as negative d upon small b and capital C as negative d upon small c. If I use these values of A, B and C in the assumption of the equation of plane as Ax plus By plus Cz plus D equal to 0, and I just rearrange the coefficients, I will get a special equation in the form x by A plus y by B plus z by C equal to 1, which is known as the equation of plane in the intercept form. Equation which is very similar to intercept form of line in 2 dimension, but here we have a z by c added in. So, it becomes a linear equation in x, y and z represents a plane. This is a special form which is to be used only if you know something about the intercepts. Otherwise, we depend on the point and the normal form. Today's lesson focused on equation of plane in vector and Cartesian form, and we covered several forms, but there is still a whole lot to learn which will be covered in our future lessons. I hope you will be there to watch them. All the best till then. Hello viewers, continuing with our series on 3-dimension geometry, we will be discussing planes. We introduced you to the concept of plane in our earlier lesson. We learned that to form equation of a plane, you must know a vector, a direction which is perpendicular to the plane, called as the normal to the plane. We also learned two very specific forms which we will continue to make use of. Let us take a quick review of those two forms. One of them, the first form that you learned, was called normal form. So, what do we know of normal form? The normal form of plane uses what is referred to as the unit normal, n cap vector. We write the normal form of the plane as r dot n vector, which is the unit vector, equal to d. D is the perpendicular distance of origin from the plane. In Cartesian, this equation takes a look of Lx plus My plus Nz equal to d. This is a very specific form because you must know the unit normal and you must know the perpendicular distance of origin from the plane. Two very specific quantities that must be in a way ready-made handed over to you, which always does not happen to be the case. So, what is the other possibility? How else can you form equation of the plane? If you know a point that lies on the plane and a vector which is perpendicular to the plane, we come up with another form which looks like r minus a dot vector n equal to 0. Vector r is position vector of any point on the plane, vector a is the position vector of a known point, and of course, vector n is the normal to the plane. In Cartesian, this equation becomes a times x minus x1 plus b times y minus y1 plus c times z minus z1 equal to 0. A, B, C are the direction ratios of the normal, x1, y1, z1 are the coordinates of a known point of the plane. If you rewrite this equation, it gives rise to a linear equation in x, y and z. Today, our focus would be on planes passing through the intersection of two given planes. When two planes intersect, they intersect in a line, and through a line infinitely many planes can be drawn. So, in a way we will be discovering the family of planes which pass through intersection of two given planes. In this figure you can see a plane pi 1 and a pi 2 intersecting in a line, and through that line I need to figure out how to find equation of a plane, say pi 3. To begin with, if I know plane pi 1 and pi 2, their equations would look like r dot n1 vector equal to d1 and r dot vector n2 equal to d2, where n1 and n2 vectors are the normals to the given planes. Now, suppose I take a point which is lying on the line of intersection with the position vector t, then t must satisfy both the equations, that is t dot n1 vector must be equal to d1 and vector t dot vector n2 must also be equal to d2. In other words, if I take t1 dot n1 vector plus lambda, lambda could be any real number, times n2, it must be equal to d1 plus lambda times d2 for all real values of lambda. Since I am interested in finding the equation of the plane which passes through the intersection and t is any arbitrary point, t is a position vector of any arbitrary point on this line, this condition has to be satisfied by all points that lie on the line of intersection, and that gives rise to a locus which is nothing but the equation of the plane pi 3, which is stated as vector r dot n1 vector plus lambda times n2 vector equal to d1 plus lambda times d2. Lambda is a real number, any real number. So, as you vary lambda, you come across the entire family of planes passing through the intersection. In Cartesians, the same set of equations translate as given two planes with equations a1x plus b1y plus c1z plus d1 equal to 0 and a2x plus b2y plus c2z plus d2 equal to 0, the family of planes passing through the intersection are given as a1x plus b1y plus c1z plus d1 plus lambda times a2x plus b2y plus c2z plus d2 equal to 0. Now, if as we start with the exercises in a little moment, you will realize if I need a particular plane, I need a specific value of lambda, and to find that value of lambda, a certain other condition must be given to us to identify that particular member of the family of planes. Well, we will be taking the exercise shortly, but one more results which would come in handy, and that is about the angle between two planes. If two planes intersect, then what could be the angle between the two planes? If we take this picture, the two planes that are intersecting are making an angle depicted by that red angle as in the figure. We want to find the measure of this angle. We say that the two planes are inclined at an angle which is defined, can be calculated same as the angle between their normals. To understand this better, let us consider another figure. Here we have two planes 1 and 2 intersecting at an angle theta. So, how does this become the angle between the two normals? In this picture, as you can see, the normal n1 and n2. As you compare the angles which this vector n1 makes with n2, you will realize that it is nothing but 90 minus theta, which of course is theta. And therefore, it is absolutely fine to understand and accept that the angle between two planes is defined as the angle between their normals. Another little thing that you must keep in mind is, if theta is the angle between the two planes, then so is 180 minus theta. We always consider the acute angle as the angle between the two planes. At the same time, if theta is now the angle which is between the two normals, then cos theta is same as the absolute value of n1 dot n2 by modulus n1 into modulus n2 vector, and therefore, theta will be nothing but cos inverse of this quantity. Also, note that two planes are perpendicular to each other if their normals are perpendicular to each other, which is same as saying that n1 dot n2 is equal to 0. And of course, two planes will be parallel to each other if their normals are parallel to each other, and therefore, this little condition comes in handy, knowing the normal of one plane giving rise to normal of another parallel plane. Now, keeping in mind the few things that we have discussed with us, I think you are ready for a small exercise. Here is our next question. It says, find the vector and Cartesian equation of the plane passing through the intersection of the planes 2x minus 3y plus z minus 4 equal to 0 and x minus y plus z plus 1 equal to 0 and perpendicular to the plane x plus 2y minus 3z plus 6 equal to 0. Knowing that given the Cartesian equations of the two planes, the family of planes passing through the intersection is same as a1x plus b1y plus c1z plus d1 plus lambda times a2x plus b2y plus c2z plus d2 equal to 0, we have the equation of the plane passing through the intersection of the two given planes same as 2x minus 3y plus z minus 4 plus lambda times x minus y plus z plus 1 equal to 0. If I rewrite this equation, it turns out to be 2 plus lambda times x minus 3 plus lambda times y plus 1 plus lambda times z minus 4 plus lambda equal to 0. This allows us to understand and identify what the direction ratios of its normal are. Now, keeping in mind that I have another plane given to us, that is x plus 2y minus 3z plus 6 equal to 0 with direction ratios 1, 2 and minus 3, which is perpendicular to the plane passing through the intersection, and therefore, the condition n1 dot n2 equal to 0 is applicable. So, if I take that into my consideration, I get a simple linear equation in lambda that gives us the value of lambda as minus 7 by 4. Substituting this value in the equation derived earlier, we get our required equation of the plane as x minus 5y minus 3z minus 23 equal to 0. Also remember that the question asks for the vector equation. So, you translate this equation into vector notation and it turns out to be same as r dot I cap minus 5 j cap minus 3 k cap equal to 23 as the required equation of the plane. Moving on, let us also look at how we find the angle between a line and a plane. So, we know that a line is intersecting a plane at a certain angle. How do we calculate this angle? Consider this picture and I think things will just fall into place. Here we have a line L defined along the vector B intersecting our given plane at a certain angle theta. The plane has a normal denoted by vector n. So, what do you see here? Is that making sense? The angle between the line and a plane is same as the complement of the angle between the line and normal to the plane. Isn't that so? So, the normal is perpendicular to the plane, line is making an angle theta and therefore, the angle between the vector n and the vector b is 90 minus theta. Therefore, if the theta is the angle between the line whose equation is vector r is equal to vector a plus lambda times vector b and plane's equation is vector r dot n vector equal to d, then automatically you will be able to see that we are only interested in not cos theta, but cos of 90 minus theta, which is nothing but sin theta, and that is the angle between the vector b and vector n, and that is equal to the absolute value of b dot n upon magnitude b magnitude n, and therefore, theta is same as sin inverse of the absolute value b dot n upon magnitude b magnitude n. Now, this result does come us in handy as we look at the applications where there is a concept of line combined with the plane. Line parallel to plane means line is perpendicular to the normal, right. Line perpendicular to the plane is same as saying or thinking of as line in the same direction as the normal to the plane. Little result, but will come in handy as we go along. Now, here is a problem for you. Find the foot of perpendicular from the point with position vector A given as I cap plus j cap plus 2 k cap to the plane with the equation r dot 2I minus 2j plus 4k plus 4 equal to 0. Hence, find the image of the point with respect to the plane mirror. Now, given the equation of the plane, I know the normal to the plane, and so in this case, if I am looking at a point A with coordinates 1, 1, 2 and from there I draw a perpendicular to the plane, we are interested in finding out the coordinates of point P. AP being perpendicular to the plane is parallel to the normal, and therefore, its direction ratios are same as that of normal. That gives us the equation of the line passing through the point A in the direction of the vector with direction ratios 2, -2 and 4. Therefore, P, which is any point on the plane, can be calculated as 2 lambda plus 1 minus 2 lambda plus 1, 4 lambda plus 2. This point P must lie on the plane. So, it must satisfy the equation of the plane. So, if I replace x, y, z with the coordinates of P, I get a linear equation in lambda, which is giving us the value of lambda as minus half. With this value of lambda, we are able to find the coordinates of the point P. In order to find the image, the only thing that I need is an understanding that image is equidistant from the plane as the point A. So, foot of perpendicular P is the midpoint, and so if I take A dash as x dash, y dash, z dash, then using the section formula, I have a simple result which helps us to say that x dash plus 1 by 2 is 0, which gives me x dash as minus 1. Similarly, I have y dash and z dash. Using simple understanding of the image formed equidistant from the plane and A dash being perpendicular to the plane, we have the coordinates of the image as -1, 3, -2. I hope today's lesson has added to your understanding of a very important concept of 3-dimension coordinate geometry. We will see you in our next lesson. Hello viewers, welcome to our series on 3-dimensional geometry. So far you have understood how to form equation of a line in space, how to form equation of plane and a few other very significant results about lines and planes. Today we are going to be looking at the condition for two lines to lie on the same plane. When do we say two lines are coplanar? Let us start with an understanding of two lines, equations given, what do we know about them? Suppose I have line L1 and L2 given to us with their equations, vector r is equal to vector a1 plus lambda times b1 vector and L2 defined as r vector equal to a2 vector plus mu times b2 vector. So, if I have a line L1 equation given, what I do know about that line is that it is passing through the point A with position vector a1 and is along a vector b1. Similarly, L2 equation given to us means that the line is passing through the point B with position vector a2 and is along a vector which is say b2 vector. From the basic vector chapter and the conditions about the cross product, we know that the vector b1 cross b2 is always perpendicular to the two vectors b1 and b2 and hence to the plane containing the vector b1 and vector b2. Knowing that the line L1 passes through A, line L2 passes through B, if I can show that the vector AB, which is nothing but A2 minus A1 vector, is perpendicular to B1 cross B2, will that then let us decide, conclude that the lines are going to be coplanar? because the vector B1 cross B2, which is perpendicular to B1 and B2, is also now perpendicular to the vector AB, and therefore, the two lines, that is L1 and L2, must be in the same plane. And that exactly is the condition for coplanarity of two lines, that is vector A2 minus vector A1 dot B1 cross B2 equal to 0 would allow us imply that the two lines are coplanar. In Cartesian, the same condition translates to the determinant x2 minus x1, y2 minus y1, z2 minus z1, second row a1, b1, c1, third row a2, b2, c2. If this determinant is 0, then the lines are coplanar, where x1, y1, z1 were the coordinates of the point A, x2, y2, z2 coordinates of point B, and the vector b1 has direction ratios a1, b1, c1, and vector b2 has direction ratios a2, b2, c2. It is a simple to use property that comes in handy. If you look at our problem here, that is exactly what it requires. We want to prove that the lines vector r equal to minus I cap minus 3j cap minus 5k cap plus lambda times 3I cap plus 5j cap plus 7k cap, and the vector r equal to 2I cap plus 4j cap plus 6k cap plus mu times I cap plus 4j cap plus 7k cap are coplanar. And not only that, the question also asks you to find equation of the plane containing these lines. So, a little extension of the problem is also added. So, how do we check whether the lines are coplanar? As we discussed just now, find the vector AB, which is A2 minus A1, and consider B1 cross B2. So, if I can show that vector A2 minus A1 dot B1 cross B2 is 0, the lines are coplanar. In this case, we have the vector AB, which is A2 minus A1, coming out to be same as 3I plus 7j plus 11k cap. Let us see what B1 cross B2 looks like. Using again the determinant form, I get B1 cross B2 to be a vector same as 7I cap minus 14j cap plus 7k cap. What do you have to do now? Verify that AB is perpendicular to B1 cross B2. So, find the dot product, and as you can see here, the dot product turns out to be 0. That implies that the lines are coplanar. But how do we find now the equation of the plane containing these lines? Remember that to form equation of the plane, the two things that you need the most, one of them is the normal to the required plane. Isn't B1 cross B2 perpendicular to the plane containing the two lines? And therefore, B1 cross B2 gives us the normal to the required plane, which we have already calculated. And so, the normal to the plane is 7I cap minus 14j cap plus 7k cap. What else I need to form equation of the plane is the point. Now, the line lie on this plane, and therefore, the point of the line, the known point of the line becomes the known point of the plane, and therefore, the point minus I cap minus 3j cap minus 5k cap lie on the plane, and therefore, using the form r minus a dot n equal to 0, we get the equation of the plane containing the lines as r dot 7I cap minus 14j cap plus 7k cap equal to 0. Isn't that simple? Very algorithmic. You don't have to think too much, but the basic understanding remains in knowing that B1 cross B2 is always a vector perpendicular to the plane containing the vectors b1 and vector b2. That is a very neat result that does come in handy in number of places. We have here another question for you, and the question says, show that the line given by the equation vector r is equal to I cap plus j cap plus lambda times 2 I cap plus j cap plus 4 k cap lies in the plane r dot I cap plus 2 j cap minus k cap equal to 3. Now, the line lies in the plane. The plane is given with a certain normal, which has the direction ratios as 1, 2 and minus 1. Now, for the line to lie on the plane, is it enough to show that the normal is perpendicular to the line? What if the line is parallel to the plane? The condition is still satisfied, but the line does not lie on the plane. So, for the line to lie on the plane, along with showing that the normal is perpendicular to the line, I must show that the point which lies on the line also is a point of the plane. Therefore, if I can show that the point A satisfies the equation of the plane and the vector n is perpendicular to the vector B, which defines the direction of the line, then our job is done. Here we have the vector n, that is normal to the plane as I cap plus 2 j cap minus k cap, vector B, which gives us the direction of the line as 2 I cap plus j cap plus 4 k cap. Simple dot product gives us 0, and therefore, the line is perpendicular to the normal, but it could be away from the plane, it could be parallel to the plane. So, further, if I take the point I plus j cap, which is lying on the line, and replace it in the equation of the plane, I get again the dot product turning out to be 3. That confirms that the point of the line is also a point of the plane, and therefore, the given line lies in the plane. I would like now you to think of an alternative. Is there another neat alternative to this problem? How do I show that the line lies in the plane? Exactly, if every point of the line lies in the plane, then the line has to be contained in the plane. If you look at the equation of the plane and the line, you will realize that if I replace the vector r in the plane with the vector r, which gives us the general coordinates of any point on the line, then if the equation is satisfied, our job is done. So, here if I replace r in the equation of the plane with the r vector of the line, I get the dot product turning out to be 3. Irrespective of lambda, the position vector of any point of the line satisfies the equation of the plane, and therefore, the given line lies in the given plane. So, that is a one step alternative to our problem. Let us take a look at another question, which is an interesting one, slightly away from the normal usual form of the questions that you have looked at in our series. The problem says a variable plane which remains at a constant distance 3p from the origin cuts the coordinate axis at A, B and C. Show that the locus of the centroid of triangle ABC is given by this equation. This expression is nothing but reading it as a 1 by x square plus 1 by y square plus 1 by z squared is equal to 1 by p squared. Now, how do we come across such an expression? Start with an understanding that a variable plane is cutting the 3 axes at the points A, B and C. So, if I take the point A to be A00 because that is the point on the x axis. Small a, lowercase a is a varying quantity, it is not fixed. Similarly, the point B where the plane cuts the y axis can be taken to be 0, b, 0. C point has the coordinates as 0, 0, c, where small a, b and c are all varying quantities. This is just one position of that plane. Once I understand the plane is cutting the intercepts a, b and c, then using the intercept form of the equation of the plane, I have the equation as x by a plus y by b plus z by c is equal to 1. Also, we have a small result which suggests that the perpendicular distance of a given point, say x1, y1, z1 from a given plane ax plus by plus cz plus d is given as the absolute value of the quantity ax1 plus by1 plus cz1 plus d by under root of a squared plus b squared plus c squared. Using this result and following the condition given that origin is at a distance 3p. So, 0, 0, 0 is at a distance 3p from the plane x by a plus y by b plus z by c equal to 1. And therefore, 3p must be equal to absolute value of minus 1 by under root of 1 by a square plus 1 by b square plus 1 by c square. So, if you apply the formula to the plane x by a plus y by b plus z by c minus 1 equal to 0 and replace x1, y1, z1 with origin 0, 0, 0, you get this result. From here, if I just square both the sides and take the reciprocal, I get 1 by 9 p square is equal to 1 by a squared plus 1 by b square plus 1 by c square. So, how do we get the centroid of the triangle in the picture? If I take the centroid of the triangle to be x, y, z, then by the basic coordinate geometry result and the of course application of the section formula, the centroid should be a by 3, b by 3 and a c by 3. Therefore, x must be a by 3, y b by 3 and z must be c by 3. So, a, b and c are nothing but 3x, 3y and 3z. So, if I know the values of a, b and c as 3x, 3y, 3z and I am interested in finding the locus of the centroid, that is a condition on x, y and z. So, what I can simply do is replace, substitute the value of a, b and c in the condition 1 by 9 p square equal to 1 by a square plus 1 by b square plus 1 by c square. So, if you replace a, b and c with 3x, 3y and 3z respectively, you get the required condition, that is the locus of the centroid as x to the power minus 2 plus y to the power minus 2 plus z to the power minus 2 equal to p to the power minus 2. With this question, we conclude our series on 3-dimensional geometry, where we learned about line and plane. Varied forms of equations of line and plane are definitely important. Simple logical understanding is used to form the equations. So, do take up more problems from your textbook and hopefully you will not have any problem dealing with any one of them anymore. All the best to all of you.
the last lecture, we discussed the variation of small g, that is acceleration due to gravity, when we go out into space or when we go deep into the earth. We also discussed the gravitational potential and gravitational potential energy. We shall start again with gravitational potential and derive the expression for the escape speed. I shall explain all these things as we go along. The potential energy we already calculated for a unit mass, which is u equal to minus g m by r. This is at the surface of the earth, and r, let me remind you, is the radius of the earth. Now, suppose we go to a short height h from the surface, then what happens? Then we can write the gravitational energy u is equal to minus g m by r. You see, m is the mass of the particle, by r. R, small r, is capital R plus h. So, r plus h. We can take capital R outside, r into 1 plus h by r, and this becomes minus g m by r into 1 minus h by r, using binomial theorem and using the fact that h is small compared with the radius of the earth. So, therefore, we can write finally the gravitational potential energy of a mass m at a distance h from the surface of the earth as minus g m by r plus g m by r squared into h. We recognize that the first term on the right as the potential energy of m at the earth's surface, this minus g m by r we have learnt already, is the potential energy of the mass m at the surface of the earth, and this extra term is g h, m g h, because of m, and this g m by r squared is g. Therefore, the extra term is m g h. Thus, the difference in the potential energy of the body as it goes to a height h from the surface of the earth is delta u equal to m g h. That means, effectively we have put the gravitational potential energy of the mass to be 0 at the surface of the earth. Remember that since it is a potential difference or the difference in the potential energy that matters, we can take the 0 of energy at any place we find convenient. So, we can fix the 0 of potential energy at the surface of the earth. Then we can call the potential energy of a particle at a height h as u equal to m g h. That is, if I take a particle to a height h from the surface of the earth, then it gains in energy, which is m g h. When the particle falls back, it gives up its potential energy in the form of kinetic or other energies. We also recall that gravitational force is a central force. It is also a conservative force. So, if we go from A to B covering a height h, then the gain in potential energy is simply m g h, does not depend upon the path taken. And if a particle falls from B to A, then its potential energy decreases by m g h, no matter what path it follows. Now, since the energy of the mass m was 0 at infinity, in the process of falling to a position r in the gravitational field, an energy equal to the magnitude to its potential energy r is released. You see, since the potential energy is g m by r, when it falls from infinity, this energy is released. We have already seen this in the earlier lecture, that when a particle falls in the gravitational field, it loses potential energy, but gains other forms of energy, including the energy that it releases. Now, for a body bound to another massive body, such as the planet bound to the sun, the total energy must obviously be negative. Why is it negative? So that we need to do work to remove this body free of the gravitational potential. So, E is equal to half m v squared, that is kinetic energy, plus potential energy minus g m m by r, and the sum of these two must be less than 0 for the particle to be bound. For example, for the earth to be bound to the sun, the total energy must be negative. So, that energy is required to be given to the earth to remove it from the clutches of the sun. Now, since the gravitational field of the earth or sun or of whatever body you consider is there and it always attracts particles towards it, is there a way in which we can make a particle free, so that it goes out of the gravitational field, say of the earth? Let us see whether it is possible or not. You know that if you throw a ball up, it always comes back. You throw and it comes back. You throw with a higher speed, it again comes back. If you throw with a still higher speed, it might go into an orbit around the earth, but it will be still bound to the earth. This orbit is within the gravitational field of the earth. So, how can we release the body from the gravitational field? We will see that we have to give minimum speed to the particle, so that it escapes the gravitational field, and this minimum speed required by a body to escape the gravitational field of the earth is called the escape speed. In fact, y of the earth from any other surface, say a particle can have escape velocity from the moon or from say another planet. So, whenever the minimum speed required by a body to escape the gravitational field of another body is called the escape speed. It is obvious that the escape speed from the earth would depend upon the mass and radius of the earth, because the strength of the field is dependent on the mass of the earth and the radius of the earth. Therefore, the escape speed would also depend upon this. So, let us write the energy of a particle on the surface of the earth. It has kinetic energy half m v squared, it has potential energy minus g m by r. Therefore, this is the total energy, and we have seen that this is generally negative for the particle to be bound to the earth. As the body gets away from the earth, its speed decreases. Why? Because remember I told you that the acceleration due to gravity is always vertically downwards. So, if the body is going up, the force is acting vertically downwards, and therefore, it will reduce the speed of the particle. So, as the body gets away from the earth, its speed decreases because of the pullback by earth's gravity. If speed of the body becomes 0 before it escapes the gravitational field, it will be pulled back by the field. You see, if it becomes 0 here, it will come back, as we do that. If we throw a ball, it goes to a certain height where its speed becomes 0 and then falls back. This happens. So, if at a finite distance from the earth, where the gravitational field is still active, if the speed becomes 0, the particle will be pulled back. However, if the speed of the body becomes 0 just when it escaped the field, it will not be pulled back. Suppose this is the boundary of the earth's field, beyond which the earth field does not act. If a particle reaches here, it will not be attracted back. If a particle is here, it will be attracted back. So, we are supposing that just at infinity, the velocity of the particle becomes 0, and it is not pulled back by the earth. So, the total energy of the particle is 0 just at infinity. Its kinetic energy has become 0 because V is 0, its potential energy has become 0 because R in the denominator at infinity becomes 0. So, therefore, the total energy of the particle at infinity has become 0. Now, the particle and the earth, they constitute a two body system, which is under the mutual force of gravitation, and therefore, the energy of this system must be conserved. The energy of the earth does not change much, because earth is a huge system, which means that the energy of the particle must be conserved. If it is 0 at infinity, it must be 0 at the surface of the earth. And what is the total energy at the surface of the earth? Half m v squared minus g m by r, and this must be equal to 0. This gives us V equal to V escape equal to 2 g m by r, and plugging in the values of g, m and r, we can calculate that V escape is 11.2 kilometers per second. It is a huge velocity, but you see it depends upon the mass of the earth or any other planet and the radius of the earth or that planet. I am showing you again by this animation. Particle comes back with a still higher speed, it comes back with a still higher speed, it comes back, because velocity of these particles is less than the velocity of escape. However, when the velocity is beyond the velocity of escape, then the particle escapes. For velocities less than the velocity of escape, it comes back. For velocity greater than the velocity of escape, it escapes, and the velocity of escape is 11.2 kilometers per second. It is remember that artificial satellites are launched with speeds considerably smaller than this speed. Why? We do not want them to escape the gravitational field of the earth. We want them to be bound to the earth and revolve around the earth. There is generally a misconception that when a body is launched with the escape speed, the gravitational field of the earth ceases to act. This is not so. The gravitational field of the earth acts at each point of the path of the escaping body, because it decreases the speed of the particle. However, the speed becomes 0 only at infinity. At that point, there is no gravitational field to pull the body back, and the body escapes. I will give you the escape speed on 3 different bodies: Moon, Mercury and Venus. You can calculate, in fact, knowing the mass of these bodies, knowing the radii of these bodies, one can easily calculate the root of 2 g m by r, and these are the speeds. And look at this table again. You see that these are very small, 2.37, 4.25 compared with, let us say, Venus 10.39 kilometers per second, or of Earth 11.2 kilometers per second. So, what is the effect? The effect is that many particles that we find in the atmosphere of the earth, they have velocities on these Moon and Mercury higher than the escape speeds, and therefore, they escape. Field of these gravitational field of Moon and Mercury is weak. The particle velocities are higher than the escape speed, therefore, they escape, which means that Moon and Mercury have no atmosphere, unlike the earth or unlike Venus. They have no atmosphere. Even on the earth, this effect is felt. Many of the light gases like hydrogen and helium are highly deficient on the earth, although they are most abundant in the universe. On the earth, they are deficient, because these are light gases. Their thermal velocities are very large, and sometimes they are larger than the escape speed from the earth, and therefore, they escape. So, during the formation of the earth, many of these gases, much of these gases, helium and hydrogen, they just escape the earth, and so the earth is deficient in these gases. Let us take an interesting case. Suppose the escape speed is equal to the speed of light. That means that the is equal to the speed of light. That means light also can escape. That means if the light escapes, what happens? There is no light from that object, and therefore, the object becomes invisible. Such an object is called a black hole. You see what is happening? We are saying that the escape speed is equal to the speed of light. That means light, the all other things can escape, but light cannot escape. That means light is bound to that object, cannot be seen from outside, and therefore, this object becomes black, and it is called black hole. So, let us calculate this speed for the sun. Suppose sun becomes a black hole someday, what would be the radius of the sun? We are assuming that the escape speed from the sun would be the speed of light. So, we just plug in the numbers, and we can find that the radius of the sun, if it becomes a black hole, is only 3 kilometers. 3 kilometers is a very short distance, but that is the radius of the sun if it ever becomes a black hole. I can assure you that the sun will never become a black hole. This is just a theoretical imaginary calculation. Sun will never become a black hole. But what happens to the, suppose sun becomes a black hole, what happens to the orbit of the earth and other planets? Remember, we saw that the whole mass of the sun or earth or other planets can be supposed to be concentrated at the center of these objects for the other objects to be revolving around them. So, whether this mass is concentrated in 3 kilometer radius or the actual radius of the sun does not matter. What matters is the mass of the sun being felt at the center of mass of the sun, and if this is not disturbed, the planets will keep on going around the sun in their present orbits. Artificial satellites. I have already pointed out that satellites are launched with velocities much less than the escape velocity. Why? Because we want to keep them in the Earth's field, we do not want them to escape, and they are usually launched from a height of about 300 kilometers. So, that the resistance of the air is small and therefore, not much energy is lost in overcoming this drag due to air, and they are launched with velocities of the order of 8 kilometers per second. So, that they can orbit the earth. Remember that artificial satellites also work under the effect of gravitational field. Therefore, whether they are artificial satellites or whether they are natural satellites like the moon, they obey Kepler's law, which is T square by r cubed constant. T is the time period and r is the mean distance from, say, for a planet from the sun, or for an artificial satellite from the center of the earth. So, T square by r cubed is constant. T is the period of the artificial satellite and r is the distance from the center of the earth of this satellite, and we can use this T square by r cubed as we use for other planets. For example, that plugging in the values, we can find that the satellites which revolve with a time period of 1 day, which are used for communication, etc., these planets, their distance is from the center of the earth, it is 6.6 earth radii, from the surface of the earth it is 5.6 earth radii, which is roughly 36,000 kilometers. So, these geostationary satellites, they are at a height of about 36,000 kilometers from the surface of the earth, or it is 5.6 earth radii from the center of the earth. The planets, the satellites which are at lower altitudes, they are only a few hundred kilometers away, say up to 1,000 kilometers away, and they move fast. Their time period is of the order of hours. You can calculate again using T square by r cubed, that their time period is of the order of hours, say 60 minutes, 70 minutes, 80 minutes, like that. In the next lecture, we intend to take the things like surface tension, the properties of fluids.
I am Anuradha Mathur. I have been teaching physics at Modern School Vasant Vihar in New Delhi. There are so many materials around us which have special properties because of their state, which is solid, liquid or gas. In the next few minutes, we will try and understand solids and a special property of elasticity. When we look around us and see the solids, they may be looking rigid and strong, while others do not. Even the most rigid rods we know can be deformed if we apply a strong enough force. We have a spring here, and if we compress it, we know it changes shape, but when we release it, it comes back to its original shape. Likewise, if we were to pull it apart, it would become longer, and on leaving it, it will return back to its original shape. I have here some dough, and if I did the same experiment with it, even with a smaller force, this is going to deform permanently. So, property of solids, by virtue of which it comes back to its original shape and size, once the deforming force is removed, is called elasticity. Also, we know that for the same solid, if the deforming force is large enough, it will be deformed permanently. It will not come back to its original shape and size, and this is the property of plasticity. Solids can be classified into two classes, amorphous and crystalline. Amorphous is when the solid molecules and atoms are arranged in a short range order. That means, in the bulk material, they do not have a patterned arrangement. So much so that they do not have a sharp melting point, and they are not rigid. Their properties are isotropic, which means refractive index and thermal conductivity would come out to be the same whichever way you measure it. These, when you break them, are not going to break with regular edges, and therefore, they have special conditioned properties. On the other hand, in a crystalline structure, the atoms and molecules have a long range order. You have a lattice arrangement in which the bond lengths, the bond angles and energies are almost fixed. That means, such materials have a fixed melting point. They also have a rigid structure, and when you break them, they break with sharp cleavages and edges. So, amorphous substances you will recognize as like polythenes, plastics, wax, and on the other hand, the crystalline structure would be with metals or inorganic compounds. To understand this as to what happens to these two types of materials, when we take some deforming force, that means an external force from outside, onto a crystalline structure, it is going to change the bond length, it is going to change the vibration energy of this particular system. So, what will happen when the deforming force is removed? They will come back to their original shape and size. To understand this a little better, let us consider a spring and ball model. In this, the ball is the positioning of the atoms and molecules, and the spring is signifying or showing the positions of bond lengths. The bond energy would be associated with the energy in the spring. So, if you were to displace any of these balls, the spring system will be such that it will try and bring it back to its original position. That means, within the setup against the deforming force, a restoring force is set up, and that is what accounts for elasticity. Robert Hooke, way back in 1635 to 1703, studied the property of springs. He loaded the spring, and the elongation of this he found to be proportional to the load he was applying to it. This later became the Hooke's law, which he presented in 1676. What are the deforming forces? How do they act? What is the effect on materials? That is what we are going to study now. Now, the deforming force will change the shape of the material, a solid structure, depending upon the nature of the material and the way the deforming force is applied and how much of deforming force is applied to it. So, the deformation needs to be measured, and to measure this we use the word strain, which means the change in configuration with respect to the original configuration. So, if you apply a force which is going to change the length of the system, for example, in this case, if I apply a force outwards, it is going to be termed as along this line and called tensile or longitudinal force. this will cause a deformity in its length. So, if I were to see it with the dough, this becomes slightly clearer. If I elongate it this way, the tensile strength is responsible for increasing its length. So, how will we measure the strain for it? It will be the change in length divided by the original length. Likewise, what would be the meaning of shear strain? Shear is a word used to talk about the deformation in the shape of the body. This will obviously depend upon how you apply the force. Supposing I get back to my cylindrical condition for this dough, and if I hold it up like this and apply a force tangential to it, the change in shape here is responsible for the shear value, the shear strain. And how do we measure it? From in terms of the deformation caused to one face of the cylinder with respect to the other and the length of this cylinder. So, change in the positioning of the top face with respect to the base and the length between the two faces. Now, there is one more way which we are going to see for the deforming force. That means, how we apply the deforming force. For our cylinder, so far we have considered tensile force, which is causing a tensile or longitudinal strain, and we have considered shearing force, which means it is causing a shear strain. The third one that we are going to study is what would happen if we compress this entire cylinder from all sides, so as it shrinks to a smaller cylinder. Obviously, this should strike you that longitudinal strains would be causing a change in the diameter. Volumetric strain, on the other hand, would cause a change in the density of this material. However, not looking at that right now, we are only considering a strain which is going to be measured as change in volume with respect to the original volume. So, we have got now longitudinal strain, the shear strain and the volumetric strain, and for each of them we have a simple way of expressing its magnitude, which is the change in configuration divided by the original configuration. Since the unit on the numerator and denominator is the same, strain has no unit for measurement. Its dimensional formula is m0, L0, T0. Now, we considered the ball and spring model, and we said that once the deforming force is applied, the spring system within the setup, which is obviously due to the bond energy, the bond length, etc., is causing a restoring force to set up inside it. That means, in response to the deforming force from outside, an internal restoring force is set up. Now, the measure of this restoring force is given in terms of stress, and we say it is the restoring force per unit area. Therefore, its unit would be Newton per meter square, and its dimensional formula would be m L minus 1 T minus 2. Now, do you think that only 3 possible ways of applying the deforming forces are there for real bodies? Not at all. You can have multiple ways the deforming force is acting on a body. Consequently, multiple strains happening, and therefore, multiple stresses taking place. But we are not going to look at that in this simplistic picture that we are considering for elasticity right now. So, is there going to be a relationship between the strain and the stress that is developed inside the body? Yes, there is. And if the deforming force is continuously increased, do you think this value of stress is going to increase continuously? No, because there is an elastic limit. That means a point up to which the stress is going to be proportional to strain, and this is called Hooke's law. So, stress is proportional to strain, or you can say stress is equal to K times strain, and so K is your measure of the ratio between stress and strain and is called modulus of elasticity. You can measure the modulus of elasticity in the lab. You can do so for a wire, and you can also plot a stress and strain curve, meaning thereby you can find the value for strain in terms of original length of the wire that you have taken, place it on a rigid support, hang some load from it, a known value of load per se, and you can find out using a micrometer how much is the extension of this wire. So, extension of the wire, which will be your change in length, divided by the original length, which will give you the value for longitudinal strain in it. Also, the load that you place for it and the area of cross section of the wire will help you calculate the value of stress, which will be force per unit area. And you can divide the two and find the value for Young's modulus, because longitudinal stress and strain are connected by a formula given by Young. Going a little further into this, you can make a graph of stress versus strain. What will this graph look like? This graph is, as you can see, has a typical look. Now, you can ask questions like, will all stress strain curves for all materials look the same? If I use a thicker wire, would my stress strain curve still look this same? Or can we draw similar graphs for volumetric stress and strain, shear stress and strain? What does the graph tell us, and how can we explain such curves? Some of the salient features of the graph are, if you look carefully, there is a region OA. The curve is linear, so Hooke's law is obeyed. Stress is directly proportional to strain. The body will regain its original shape and size. Once the deforming force is removed, the solid behaves like an elastic body. AB section of the graph, stress is not proportional to strain. The body returns to its original shape once the deforming force is removed, because you have yet not deformed it completely. Point B is the yield point or the elastic limit. The corresponding shear is called yield strength, and this is the limit or optimum deformation that this particular system can withstand. Look at the portion BD. The stress developed exceeds the yield strength, and the strain increases rapidly even with small deforming force. What does that mean? That means that the material is going to have more and more strain even with very small deforming force. That means the stress within it is not at all proportional to the strain. At C, the body regains the dimensions, though not exactly, and that is with permanent deformation. This is a deformed condition and we call it plastic deformation. D is ultimate tensile strength. Beyond this point, additional strain occurs with small deforming forces, and point E makes it a point of fracture. That means the material is going to snap apart. It will break into two pieces and therefore will not remain as one unit. So, brittle materials have points D and E which are close to each other, but a large separation between D and E is suggestive of ductile materials. These are the ones that are used for making wires, rods, ropes, etc. So, we have seen that we can place solids in two categories, which will be crystalline and amorphous. Crystalline structures have a regular arrangement of atoms and molecules within them, and that they have regular values of bond length, bond energies. A slight displacement in them by an external deforming force causes this entire setup to be changed. A force of attraction or repulsion results between the atoms, which is the cause for elasticity. We have also seen how we measure this elasticity in terms of deformity created, which is our strain. And we have also checked out that the restoring force which is developed within the body is basically the force per unit area. So, stress is not the same as deforming force, but deforming force per unit area within the elastic limit is the value for stress. You can plot a graph between stress and strain, and that graph has a peculiar shape. You learned the salient features of the graph, and you have also seen that you can find out a modulus of elasticity, which is a measure of the ratio between stress and strain. You also learned the units of all these values. Strain has no unit, stress has a unit of Newton per meter square, and the modulus of elasticity also has a unit of Newton per meter square. In the next episode, we are going to learn more about elastic moduli. We are going to learn ways of finding modulus of elasticity and some applications with the materials around us on the basis of elasticity. Engineers and product designers make use of this knowledge about elasticity of the material and choose it for different purposes, making bridges, making trolleys, making shoe soles, making tires. All of this means you must know the elastic property of that material in that condition, and that will be the way for making new things, new innovations for useful purposes. I am Anuradha Mathur. I have been teaching physics at Modern School Vasant Vihar in New Delhi. In our previous episode on solids, we learnt about their internal structure. We learnt the attractive and repulsive nature of intermolecular forces were responsible for the property of elasticity, which is a deforming force is removed from any solid, it regains its original structure. This fact could not go on beyond a particular point. That means, you could not endlessly increase the deforming force and expect the body to come back to its original shape and size. You will also recall that we looked into words like deforming force, which were external forces which were acting on a body. Now, these were such which depended upon the nature of the solid structure, and therefore, you categorize them into three classes. We said if the solid has more length like the rope, then you would be talking about tensile deforming force, and consequently, the restoring force which developed inside it per unit area, you called it stress. The measure of how much of deformation took place along its length was longitudinal strain. Likewise, you also studied about solids for which deformation took place because one particular section of it was displaced, such as in this case of a book, where if you were to deform it by pulling only on its surface, it would deform with a shear force. The base of the book remained where it was, and the displacement on top with respect to the base would be your shear strain, and you could measure shear stress. This was done with solid structures like this mentioned in your books, which had a geometrical shape because it was easy to calculate the area. You also studied about volumetric stress, which would happen if the deforming force was hydraulic in nature. That means, say for example, on a spherical ball like this, if the deforming force was from all directions, that means a hydraulic pressure was acting on it, whereby the ball would shrink in its size, its diameter becoming smaller, but its shape not changing. That would account for volumetric strain, and the internal stress developed per unit area in it would be termed as volumetric stress. Now, we are going to look at the ratio of stress and strain, which according to Hooke's law should be related. We did a graph for that in our previous episode, and we are going to now describe the modulus of elasticity. So, tensile modulus of elasticity is called Young's modulus, and it is measured as the ratio between longitudinal stress and longitudinal strain, and it would be given by F upon A divided by delta L upon L, and it has a unit of Newton per meter square, and its dimensional formula would be m L minus 1 T minus 2, which is same as that for stress. Now, if you look at some of the common materials that are around us and study their Young's modulus, notice that the order of magnitude is 10 raised to power of 9 Newton per meter square, which is a very large value. So, if you look at steel, for example, it is 200 into 10 raised to power of 9 Newton per meter square. In the same table, you can also see the elastic limit value and the tensile strength. Notice for bone you have got two values given, which are given in terms of tension and compression. That means this is slightly different, and this should be taken into account if you were to measure the elasticity for bone in order to know why a fracture takes place or how you can make a pyramid. So, when you are asked a question which is more elastic, steel or rubber, obviously steel is more elastic as compared to rubber. Why? Because you can break a rubber band by just your hands, but it is not possible to do so for a metal wire. Bone structures, as we were talking about, you must have seen in the case of pyramids, where you have people one on top of the other, and at athletic meets, etc. These kind of structures are often done in school, but you must have seen that only very strong people go below, and the people from junior classes with lighter mass of bone and lighter weight go on top. Engineers and product designers need the value for y. How do we determine the value for y in the lab? It is done by using Searle's apparatus. In Searle's apparatus, you have two wires of about 1.5 meter in length, and let us say you mark one of them as A and the other as B. A is called a reference wire, and attached to it is a weight so that it remains taut all the time, and wire B is the one on which you apply some load, which will cause it a tensile deforming force. That means trying to elongate it. A micrometer is used in order to find how much of elongation is taking place with respect to wire A. And having gotten all this, you can therefore find the diameter of the wire and calculate the restoring force which is set up within the wire B, which would be your stress, and then calculate the value for y. And so, your working formula would be y is equal to mg into L upon A into delta L. Shear modulus, on the other hand, is represented by G, and it is given in terms of shear stress and shear strain. So, how do you measure this thing? This is a very simple example here, in which only one portion of it, that means the top layer, is say moved, say boxes, cartons, etc. like that. So, what do we do? You can measure it in terms of, say you have this book and you keep this edge of the ruler alongside its beading, and when you pull only the top cover by using suitable force, you find it is displaced to a certain extent. This displacement can be measured, and you can also find out this surface area by multiplying the edges and finding a product for that, the value of your force is known. So, the shear force can be calculated, and therefore, you can also calculate the shear stress and the shear strain. So, you have seen you can find the value for G in the lab for some objects which are not so rigid, and you find that its value is given in terms of Newton per meter square. Its dimensional formula remains m L minus 1 T minus 2. Looking at this chart, you will see that for most of the materials, this value of G is almost 1/3 the value for Young's modulus. That means, if you had a plastic cube which was solid and you were finding out its Young's modulus, then it would have a certain value, and if you did the same for shear modulus, it would be 1/3. So, the same material will have different values for Young's modulus and shear modulus. Let us take up a problem. If you have a square lead slab of size 50 centimeters and thickness 10 centimeters, the lower edge of which is riveted to the floor, a shearing force of 9 into 10 to the power of 4 newtons is applied on the narrow face. How much will be the upper edge displaced? You can visualize it something like what we did with the book, and when you solve it, you are going to find that this displacement is 0.16 millimeters. So, this value is very small and has to be carefully measured. However, when you do this problem, it gives you an idea about how much of shearing force is required if you want anything to deform or if you do not want it to deform. Next, we go on to volumetric stress and strain. The ratio of volumetric stress to volumetric strain is known as bulk modulus. It is represented by B, and it is very special. Notice, if I were to give this ball a hydraulic deforming force from all sides, I am going to diminish its size. That means, I am going to make its volume less. So, positive pressure on it is going to make its volume become less. Therefore, the value for B is associated with a negative sign. It is given as B is equal to minus P upon delta V upon V. The rest of it does not change very much, and this value is given in terms of Newton per meter square, and it also has the same dimensional formula. Bulk modulus of some of the materials are given: aluminum, brass, copper, same as those were in the earlier list, including steel. But there is no such straight relationship between bulk modulus and Young's modulus as we had seen in the case of shear. Compressibility is another very important value, and that is 1 upon B. It is the fractional change in volume per unit change in pressure. These are some of the moduli that we consider for solids. In real life, how is it important to us? Let us consider the chairs that we sit on, the shoes that we walk on, the flyovers or the bridges that we step on. All these things are engineering marvels, you can say. You can change the value of Young's modulus by changing the value of the material that it contains. For example, tires etc. that are used for vehicle are all made of rubber. They are the same as the eraser that you use in your geometry box, but they have a content of carbon which is designed to take on the weight on the road of the vehicle and designed to take the elasticity with the bumps on the road, etc. One of the other things that you need to see is that how does this elasticity change the way we design things. For example, the ropes that are used for cranes, they are not solid, they are made up of thin wires. Why that is required? Let us see from an example. For example, if you had to lift say 1 ton of material or a box which is about 1000 kg, then your requirement for steel rod would be about 6 centimeters diameter, which is reasonably high, and therefore, this would be solid and not flexible at all. So, what is done is that you have this thin wires like this, which make up the entire rope in this manner. That means, you do not compromise on the strength of the rope, and you change it by making it as a composite unit of thin wires, so that it has its flexibility and it can be used wherever you require it. Beams are used in bridges, in flyovers, railway tracks. Why is that? Because you do not want the load that comes on it occasionally, that means with traffic, when the load comes on it, it should not buckle under that. Therefore, I-shaped beams are used. That is a special design which is ready to take on the deforming force and develop the requisite value for stress within it, so that for small strains it is able to maintain its elastic property. You do not want any of the bridges collapsing. One other example which strikes us, ordinarily we do not think about it, are the sand piles or the gravel piles at the construction sites. When it is loaded off from a truck, it piles up in a particular conical shape. Why is that happening? This is because of shear property. How does shear come into the picture? We are going to just look at it from this example. Why is the height of a mountain a certain value? Why aren't all mountains higher than Mount Everest? Why is Mount Everest so unique? What happens is that the weight of the mountain falls directly on its base. The sides of the mountain are free, and because of this it is not a case of compression. So, what happens is when the weight falls on the base, the sideways force starts off as stress. So, the stress between the rocks or the rock material at the base is responsible for how much of force it can withstand from above. That means, the deforming force that accounts for its height. Now, let us calculate the highest height that you can have for a mountain on earth. This maximum height calculation is not that difficult. We are going to do it in a very simplistic way. Let us say that the elastic limit for a typical rock is 30 into 10 to the power of 7 Newton per meter square. So, to calculate the weight of the mountain, we will need its assumed height and the density and g. So, we will assume that the density of the material of the mountain remains the same, which let us take it as 3 into 10 to the power of 3 kg per meter cube, and let us assume that the value for acceleration due to gravity also remains the same and does not vary with the height, which it does. So, with all this assumption, we can calculate the value of h, and that will be 30 into 10 to the power of 7 Newton per meter square divided by 3 into 10 to the power of 3 into 10, and that will give us approximately 10 kilometers, which is more than the height of Mount Everest. That means, you cannot have a mountain on earth, if these were the specifications, higher than Mount Everest. Why is Mount Everest only the highest one? Why aren't there mountains like this all over the world? They could have been, there are mountain ranges, but perhaps the shear force does not allow this height to be placed on any other portion of the earth, and that is why Mount Everest is the highest. So, today you have seen in this episode with solids the 3 moduli of elasticity, which were for 3 special shapes, one more in length, which were like rods and wires or thin strips of metal. The others were solid structures like for boxes or say solid square pieces or rectangular cuboids like that, or shaped like a sphere like the ball that we had considered. So, therefore, you can find the value of elastic moduli, have a comparison for a particular object. You can also find this by doing suitable experiments, and Then we went on to see some applications in real life using the modulus of elasticity or our small knowledge about elasticity. After all, there is a lot to learn about mechanical properties of solid vis-a-vis elastics and plastics.
Till now, you have studied about the transport of water in short distances. Now, let us study today long distance of water in plants. Have you ever placed a twig bearing white flowers in colored water? What do you observe? You observe the flower becomes colored. What is the reason? Today, we are going to find out the reason for that. It is due to the process of translocation. Let us define translocation. It is the bulk movement of substances through vascular tissues in plants. Now, let us see what is bulk movement. Bulk movement is the movement of substances in mass as a result of pressure differences between 2 points. Now, let us see how the bulk transport takes place. It takes place through 2 vascular tissues, xylem and phloem. In the xylem, the transport takes place through roots, and in the phloem from leaves. In the xylem, the transport of water and mineral is from xylem to the other aerial parts that include water, mineral salt, organic, nitrogen and hormones. On the other hand, in case of phloem, the movement of water and minerals from leaves to other parts of the plant body, and that includes inorganic and organic nutrients. Now, let us see absorption of water and mineral solutes. How does it occur? It occurs to 2 pathways, which are apoplast pathway and symplast pathway. Let us see the differences between the 2 pathways. In apoplast pathway, it consists of cell wall and intercellular spaces. On the other hand, in symplast, it consists of cytoplasm connected with plasmodious matter. In apoplast, water does not enter living cells. On the other hand, in symplast, it enters living cells. Apoplast, fast movement of water molecules. On the other hand, in symplast, there is some resistance. Apoplast pathway is not influenced by metabolic activity of root. On the other hand, in symplast pathway, it is influenced by the metabolic status of root. Now, the 2 pathways can be explained with the help of the following diagram. In the diagram, you can see the blue colored that represent apoplast and the other light color that represent the symplast. So, in the apoplast, the water moves outside the cell. On the other hand, in symplast, the water moves inside the cytoplasm. Now, there is another important phenomena that we see in the plant is mycorrhiza. What does that mean? Myco means fungus and rhiza means root. There are certain fungus which are associated with the roots of the plant, especially the forest trees. The following diagram, it shows how the mycorrhiza helps in the absorption of water. The diagram shows the infection thread that invades the cell of the root. Now, when we study the movement of water up the plant, there are 2 widely accepted theories. One is the root pressure theory, and the other one is the transpiration pull theory. Let us study the first theory, that is the root pressure theory. This involves positive pressure and the movement of the water molecule to small heights. Now, this can be demonstrated by drop of solutions when the oozing out of soft stem plant when cut. It cannot explain the transport of water in the tall trees. Root pressure theory can be demonstrated by a simple experiment. Now, what do you see in the diagram? In the figure, you see a watered plant which has been connected with a manometer to measure pressure of exodus from cut stems, and the adjacent diagram that shows the exudation that demonstrate root pressure. Now, let us study the effect of root pressure. Now, have you ever seen a nasturtium leaf? Early in the morning, you can see some drops of water. What is that process called? Yes, the process is called guttation. So, if we define the guttation as the exudation of watery drops from the edges of leaves and uninjured parts. Now, these leaves, they also contain some pores, but they are definitely different from stomata. What are they called? They are called hydrathodes. Look into the picture, you can see the structure of the hydrathodes. The hydathode, it contains a cuticle covered with a sheath and an epitheme which contains loose cells, a water cavity inside that is continuous with the xylem, and at the upper part you can see the stoma. So, the water exudes out of the hydathode early in the morning. Now, let us study the other theory, and that is the transpiration pull theory. It was proposed by Dixon and Joly in 1894. Transpiration creates a pull over water column which is lifted upward like a rope and is not broken due to presence of strong cohesion force amongst the molecules. Under transpiration pull theory, there is ascent of sap, that is the movement of material and waters. Now, let us study what are the physical properties of water that is responsible for the transpiration pull theory. There are three important properties. The first property is cohesion, which is mutual attraction between water molecules. The second property is adhesion, that is attraction between water molecules to polar surfaces. And the third, surface tension, the water molecules are attracted to each other in the liquid phase. So, now these three properties, cohesion, adhesion and surface tension, how does these properties affect the plants? So, the two important effects are there. Number one, high tensile strength, which is ability to resist a pulling force, and second, high capillarity, this ability to rise in thin tubes, example in this case the tubes and vessel elements. Now, before we going into the detail of the transpiration pull theory, it is necessary to have a look into the internal structure of leaf. You can see in that following diagram, the leaf having an upper epidermis, palisade mesophyll, spongiphyll and the lower stomata, which help in the exchange of gases carbon dioxide and oxygen. The following diagram very well explain the transpiration pull theory. If you look into the picture, you can see the absorption and correspondingly the transpiration. So, the transpiration, it helps in the absorption of water into root. In the diagram, you can see the water absorbed by the root hairs and moving up into the mesophyll of the leaves. So, transpiration by leaves, it helps in the absorption of roots. There is another very important phenomena that you have studied in earlier classes also. that is transpiration. You can see the water in the form of water vapor lost from the surface of leaves through the stomata, which is generally present in the underside of the leaves. To understand transpiration, let us have a look into the detailed structure of stomata. The stomata, you can see the two guard cells. Look into the picture and we see the microfibrils which help in the opening and closing of stomata. The opening and closing of stomata is due to change in turgidity of guard cells. A very important thing that we can observe in the stomata is the inner wall thick and elastic and the outer wall thin. When the turgidity increases, the outer thin walls bulge out and the cellulose microfibrils help in the opening of stomata. The following diagrams clearly explains the opening and closing of stomata. During opening of stomata, you can see the guard cell absorbs water, the pore opens and the stomata is opened. On the other hand, in the case of closing of stomata, the water oozes out and the guard cells become flaccid and the stomata closes. Now, a very important question might bother you, that how water reaches leaf parenchyma cells. So, it is through the evaporation of water through stomata which result in pulling water into leaf from xylem. Second, the low concentration of water vapor in atmosphere as compared to the substomatal cavity causes water diffuses into the surrounding air. In the following diagram, it is very well explained how the water reaches the parenchyma cells. If you look into that diagram, you can see the soil water which enters into the root through root hair. There is osmosis cell to cell, and then the water moves up to the xylem vessel in stem or root, and finally to leaf, enters into the palisade, and there it is absorbed and used in the process of photosynthesis. And then we see the transpiration photosynthesis compromise. How the transpiration compromises photosynthesis. Look into the picture. You can see here carbon dioxide is taken inside by photosynthesis and water is given out by transpiration. Now, let us see what's the importance of transpiration in plants. It creates transpiration pull for absorption. Second, it supplies water for photosynthesis. Third, transport minerals from soil. And the fourth, it maintains shape and structure of plant by keeping cells turgid. So, now let us summarize the topic. The long distance transport of substances in plant takes place by the process of translocation. Second, there are two important pathways for the absorption of water. The one is apoplast pathway and the second one is symplast pathway. There are two important theories that we have learned today. One is the root pressure theory and the transpiration pull theory. And the last, the effect of transpiration in plants.
मित्रों, आपको हमारे कार्यक्रम कैसे लगे? आप अपनी प्रतिक्रियाएं और सुझाव हमें भेज सकते हैं। हमारा पता है किशोर मंच, CIET NCERT, श्री अरविंदो मार्ग, नई दिल्ली 110016। आप हमें ईमेल भी कर सकते हैं। हमारा ईमेल पता है ciet.kishoremanch@gmail.com और हमारे टोल फ्री नंबर हैं 1800111265 और 18001112 199।